are like 3.5 hours long. I would like to try to cut them down into like segments so it's not just a 3-hour block where you have to go through. But hopefully I can give you that as a resource by the end of class. But we're not going to. I'm probably not going to upload them anywhere like by the next day, unless you really really want that. No, I mean later you can go back, that kind of stuff. Okay. So we're back on the data summarization lab. The key should be on the website. If you can't see the key, let me know, but it should just be there to grab. So we talked about, we're still talking about the bike lanes data set from Baltimore. So we're going to, again, load up our libraries that we need. We're using readr to read the CSV, dplyr to do some of the data manipulations, and also the pipe, the % greater than %. So we covered a lot of these different things, up to number 4, I believe. So, excuse me? What is in the key? The key doesn't have anything beyond number 4. No, it's data summarization. Sorry. So it should be on the website. Yeah. All right. So I read the data in. So again, let's take. So either we can use head to get a gist of what's going on here, or we can use view to get a better look at what the data really shows us here. And we see something really interesting. Date installed. So some of this data in the CSV, we didn't. The lab doesn't expect you 100% to do all the cleaning or anything like that, but we do expect whenever you read the data set in. First step is always just take a look at it before you do any models, any summarization, unless it's like a summarization that's part of data cleaning. Take a look at your data. As a statistician, data analyst, data manager over the years, I can't stress that enough. Things, your brains have evolved over thousands of years to really identify patterns well, visually. So things like this, just taking a ballpark look at it, not even looking at the individual inputs in the data, you see there's missing stuff. You see this, and it's built so it shades in a different way, it looks a different way. You see there's missing data here, right? So also, looking at this specific data, give me some input, give me some oddities about these 2 columns, the last 2 columns, date installed and length. Something weird about date. You see a 0. So, some data manager, some database person, or somebody in the city who makes this bike lane data set, for some reason, instead of putting missing or putting like some indication that it was before a certain date, they put 0. Don't know why, but that's the way it was coded. But that's this is a 2,000-year-old bike lane, right? Year 0 is just missing, right? So we can recode that. Second thing is, what's a weird thing we see about length? You got a 0. It's not a very good bike lane if there's no length to it, right? You just start and stop, bike lane over. So, these are some things we're going to talk about today, how to identify these, how to clean some of these things. And in the key, we do one thing. What was the average bike lane length per year that they were installed? Set bike date installed to be NA if equal to 0. So there is code in there to do that, but I want to do it the way we had spoke about yesterday. Date installed, bike date installed equals 0 equals NA. Right? So given what we showed yesterday, this should make sense. The dollar signs grabbing the specific column, we're just using an operator to say, is it equal to 0 or not? We're putting a bracket around it because we want to do, so we're reassigning things. So we're taking this column, bracket to say we only want to change these specific things, and we want to find when it's equal to 0, we assign it to NA. Is this statement clear? Is that a yes or a no, or like it's somewhat clear? I assume that's probably the consensus. So if we run that, right? Sorry, I'm going to read the data back in really quickly, just because I want to show you what happens when we do table bike date installed. Sorry, date installed. Right, we have the 0, and then after we run this command, we run this again because table by default doesn't show missing, it's gone there. But if we say use NA, if any, we see that those 126 year zeros are now encoded as missing. Okay? We could have changed it to something else. Yes?
What functions does use NA work in? As opposed to, there's all these different things for dealing with NA. Because I feel like I kept trying that or variations of it, and sometimes it works.
So that is dependent on the function. You have to look at the help file. So almost all the summers. So use NA is not a common one. Use NA is a very specific one to table. We'll talk about today, about like 3 things. One, use NA is more or less specific to table. NA.rm is much more common. Okay. The third option is to explore your data and either change NAs to something else, right? Sometimes you want to call this missing or something else like that. But that's not helpful that's not useful for numeric data, for example. So the NA.rm is the most common, is the one that's I would say most standardized to be used. The other way you can do it is you can run a command where you subset where things aren't NA. Right, so we're going to talk again a little bit in more detail today, the is.na function.
So the subset you just do like the filter?
So not filter. So if it's on a vector, so filters and all the dplyr commands work for dplyr commands. So yes, you could do that. You could filter and then run. But what I was suggesting, for example, is if you say table, we'll talk about, again, is.na. So you say run this command, but subset the ones where it's not missing. This is essentially what na.rm does, but all I'm trying to say is the summarization commands and the table commands don't necessarily link up. The syntax isn't the same, right? But I'm saying you can either do the na.rm equals true, or you could specifically, explicitly subset the cases, let's say of the bike installed, where it's not missing. This isn't a good example. Let's say we take the mean length. So this is the mean length for the bike lane length in feet, or I believe in feet, where you're not missing the date installed. Does that make sense? Okay. So we'll talk again about is.na a little bit more later. But this is one way where we've shown so far you can take a specific value that you want to replace and turn it to NA. Okay? We are going to talk about other conditions or other functions, one of them being if-else today, that allow you to do this a little bit. I don't know if it's more intuitive or more straightforward, but it will be. We will show you how to do this for how to replace things with something else. Also, when we want to create factors or levels and stuff, we're going to use that later. Okay.
Just a question.
Yes.
On line 63, I didn't hear the statement you made. What does that mean?
So this is, we're grabbing the vector for the length. We're subsetting it on only cases where they're not missing the date install.
Not missing.
So we'll talk about this today, but not, so is.na will return true if it's missing. This exclamation point will reverse that, make it true to false. So this is not NA. And then it'll subset those and then run the mean function on that.
Okay, my confusion is, when I see equals to true, not here, the earlier ones, like yesterday, where we equated
Yes. So I think if let me respond, and if this is what you are getting at, let me know. So you don't do this, right? So this is not so.
Why doesn't that?
That doesn't work because we don't. Well, one, that's how R works. But the real thing is that test isn't well defined. So let's say, so we have no idea what this is. This is unknown. So you're saying is something equal to an unknown thing? And the answer is, I don't know. Right? So if you try this, right, it'll give you back NAs for every single value. So it's a quirk of R. A lot of new users starting out try this. It's just not the way it's done for missing data. Missing data is handled differently. Because let me give you an example. We have two ages that are missing in a data set. One person is 30, the other person is 31. Okay? So, but they're both missing, but the actual value is completely different. Right? So if you said, like, is missing equal to 30, right, although it's not in your data, it's missing in your data, in the real world, one of them it's true, the other one's false. But you can't tell because it's missing. Right? So all I'm saying is, at the end of the day, missing data is treated differently. You have to use these is.na functions if you want to do this operation. This is not how you do it. And you don't, and similarly, you don't do this, right? You actually use is.na, bike installed, and you just, sorry, it's kind of falling on a crack. So missing data, in every language is treated differently. R treats it this way where it's kind of conservative in the sense, if you do stuff with missing data like this, it will be conservative in the sense that it'll make everything missing. So I mean conservative in the sense that if you try to do things with this, you should get answers that, one, are very strange, or two, look completely wrong, or three, are all missing, right? So missing data is handled differently than just numeric values. So we'll talk about is.na a little bit more. All right, so what is the average bike lane length per year that they were installed? So we give a bunch of different answers. This is the one I'm going to focus on because this is the one with the dply array. There are other ones that we show up here. I'm not going to go over those necessarily. That is in a different syntax, but we showed you a different way to do it. But for consistency, for learning, for saying this is the way I would do it, this is where I would look. We take the bike data set, we pipe it, and we group it by the date installed. Okay? So 2010, 2011, 2012. So when we do that, I'm just going to print this out really briefly. One thing you should note. It says groups. It is a grouped data set. Right? So it's grouped by this variable. Okay? So when we go to summarize it, which is what we're going to do now, it will do things by the date installed. So 2006, there's only 2 bike lanes, around 1,400 feet in average length. All right, so just took 2 numbers and added them. 2007, there were much more. 2006, 2009. So the ones that were, let's see, the ones that were installed in 2009 for some reason were on average longer than the rest. But for the most part, you know, every year, it didn't matter. It doesn't really seem to be a case where, you know, they're installing longer bike lanes or anything like that, right? Because there doesn't seem to be a clear pattern that, you know, this is increasing or decreasing or anything like that. So it doesn't seem like the average length of bike lanes, no matter how they were installed, it doesn't depend on the year. right? So group it, then we summarize it. And again, you can use Z or S for summarize, whatever one makes sense. So again, we define it, we say a new variable n, and we want to count, right? So n, this n function is counting the number of records. And then we say we want a new column named mean, and it equals the mean length. We can call that anything we want, mean of the bike. We can call that whatever we want, and that'll be defined as the new name of the variable. Okay? Okay. Let's describe the distribution of bike lane lengths. Okay? So quantile, right? We'll give you just a snapshot. I'm gonna pull this up. Quantile. All right, one thing we see off the bat, again, we already talked about this. The minimum is 0. That's weird. That shouldn't be the case. That's either a coding error or missing, but that's the way it's coded up. We can also say hist, and I am going to use zoom. So there's a zoom button, and I'm going to do that a lot because when you make RStudio really big font, it doesn't do super well with kind of plotting it down there. So you can go here, zoom around. Okay, so there seems to be a couple bike lanes that are really long. Right, so it's a heavy tail distribution to the right. But this doesn't give us a good idea as to what's going on here. So sometimes, if I'm going to look at the help for hist. So by default, it does some method to estimate the breaks. So you could either give the breaks that you want to give. So let's say every 100 feet. Or you could give it how many breaks that you want. So here, I'm going to say I want 100 breaks. So this is how it looks. So it looks a little more different because we have smaller bins, right? So it looks like a lot of them. I don't know. So here's 1,000, maybe about 500, maybe about 250. 250 on average, right? But again, we see some way in the tails. So if we see something like this and we don't think this is correct, then we can do filtering based on, bike length greater than 2,000, see which ones of those, and explore that data a little bit. Okay? And here, we do the same thing, just we log2 transformed it. Right, just to give a better idea, I'm going to actually do log 10 because that might be make a bit more sense. They're going to look pretty much the same. So 2 means 100, right? 3 means 1,000. So we log transformed at base 10. So this is 10 to the 2, 10 to the 2.5, 10 to the 3. That's kind of the data we're looking at. Looks a bit more unimodal. I wouldn't say normal, but it looks unimodal and relatively symmetric. So that can give us a gist of what's going on. But again, the raw data does tell us that some are way higher than the rest. Nope. Sorry about that. All right. So describe as above after stratifying by the type and the number of lanes. So in this, you could have done that a lot of different ways. So I'm going to show you some box plots. Then I want to get your input. How would you want to summarize this data? And we'll show you how to do that. And I'll post up the code afterwards. All right. So here we're going to say box plots. So this is by the quote unquote type. You'll note that some of these things, they're long and they seem to bunch together, it won't show every single tick. We can have that behavior changed. We can change the size of it. We'll do that later in a visualization lecture. But here's the values on the y-axis. This is stratified by the different types. We see this type, I make this smaller, let me go back to 0. So nope, it's not going to give us that. So we see that these two, for example, signed route has a lot of these things in the way tails. So it's just a box and whisker plot, right? It's calculates outliers the same way that almost every single stat software does. Is it takes the IQR, right, the difference between the 75th and the 25th percentile, multiplies that by 1.5, adds to the 75th percentile. Anything above that is called an outlier. Anything below that is called an outlier. That does not mean the data is not right. Pretty much box plot outlier definitions are useful for normal-ish data, symmetric data, right? This data is very heavy-tailed to the right. Using that as a criteria for an outlier is probably not too good. So let me get this back up. Yes?
It didn't print all the, like the types on the bottom.
Yep.
So it's something you can do that.
Yeah, we're going to cover that in the visualization lecture, but this is one of the ways you can also do it. So there's an option called LAS, which will print the bike lane. It'll rotate the ticks, right? We can change that to like 45 degrees to get them pointing down like this, and I'll show you that in a second. But this is the bike lane, bike type, or lane type, sorry. If we run the same exact command, I think with 2, nope. Oh, no. So we're going to show you how to do that in ggplot2 anyway, so I'm not going to necessarily go into that right now. You can tell the angle in some other way. But okay, so this is how many lanes are in the bike lane, or in the bike path, or whatever. Right? So if there's 2, there's 1, there's 0. Again, num lanes equals 0. That's a question I'll go back to the data manager and say, what does that mean of 0 lanes? Right? Similarly, I'd go back and ask, what is a bike length of 0? What is a date installed of 0? What does that mean? And if you don't have someone to answer that question, you have to make some sort of judgment call, right? But again, if we do these box plots, let's do the same exact thing we were talking about before.
So
Yeah.
what is it doing with our missing data in the box plot?
Box plots, it's dropping it.
Just the default is to remove them?
So there's no other way to plot them,
Okay.
right? So you'll see I log 10 transformed it, and I got an error, and I'll talk about what that means in a minute. But this is kind of looking at the median on the log scale, right, of the data. So it looks like side path is a bit higher, right, than the rest of them for some reason. But this is kind of some of the quick things you can glean from the data kind of going forward. So, 2 things. 1, you'll see outlier negative infinity is not drawn. I did log 10 on a variable that has length of 0 in some of these cases. When you do log of 0, you get negative infinity. So a lot of times you want to do, if you want to keep the zeros, you might add some sort of additive. Usually it's 1, just so that when you add 1 to 0, you get 1. You take the log of 1, you get 0. Right. Okay, so you'll see the side path, there's one case that actually had the bike lane length of 0.
So even if there was an error, the plot is still part of the.
So it's not an error.
Oh,
It's a warning, right? But yes. So to answer your question, let's just make one of these. I'm gonna make one of these missing. Right? Still plots, just drops those data points. You have to, because it doesn't know where to put them in the plot, right?
But it doesn't like report a number. What if can you get it to report a number missing like the way in SAS it tells you?
You have to do that yourself. You have to add text to the plot. Okay. Similarly, let's go back to this. So we showed the. That's just our studio thing. So you use tapply, get the quantiles or something like that. That could be a different way. So this code right here we're taking the length vector, we're using type, and we are running the quantile function on there. Summarize doesn't work super nicely with things that return more than one number. So, for example, I say summarize. We want to go by type. We want to group it by type. If I say Q, I believe this will not like it. Okay. Well, it doesn't like it if you don't spell things right. That wouldn't have errored before because it didn't have an NA, but I just put one in there. So if you wanted something like probs equals 0.7, right? And I'll write up a little blurb on how to get this to do something where it returns. So quantile on default returns 5 numbers. Summarize expects it to summarize the data. It expects it to return 1 number. So here I'm just saying let's get the 70th percentile. But I will show you tomorrow how to kind of use summarize to give you more than one thing back. But okay. So that's one way if we wanted to get the quantiles, we could copy and paste this over and over again. Get the 25th, whatever quantiles we felt like, and make new variables over there. Okay? Alrighty. So we're going to talk about data classes and some missing data. And then we're going to jump into data cleaning. And then we're going to hopefully take some questions on like, how do I clean like this? How do I do this? Alright. So we talked about data types before, right? We talked about all the different types. Characters, strings are individual characters. Quoted, numerics, the real numbers. So there is a specific type in R that isn't just a numeric. It's an integer. An integer is just a whole number. We're not going to use these for the most part, except in 2 usually specific cases. When we use the sequence, the seq function, or the colon operator, 1 to 5, those are technically integers. And when we use indexing. So what will happen when we try to say x bracket 1, that'll work just fine. It'll treat 1 as an integer. But if you said x bracket, let's say, x bracket 1.5, x is it will still give something back. So what I mean by that is, when you're doing indexing, you should be using whole numbers. But even if you don't, it will give something back. It'll take away anything. It won't round. It'll truncate the decimals. But for the most part, if you're doing indexing, you should be either using which, or you should be using a sequence of numbers or a sequence that you've generated, not some sort of numeric number. Okay. That being said, if you subset based on logicals, like logical conditions, using filter, it's not going to be a problem. Okay. Factor. So we're going to talk about here categorical or qualitative variables. So a lot of times we talked about characters, right? But how do you use, variables that are like, for example, marital status, which has multiple categories, which we don't want it to treat as a string. We want to put that into a model, for example, and we want an indicator for each different type of marital status with some sort of reference, right? Factors is the way we do it. We've talked about logicals a bit here and there. And because there are some other types, we have to talk about dates, I believe. Because, again, if we're talking about public health data, dates are in there. Dates are in almost everything. All right. So again, we showed this before. Character and numeric types. If you say class, it says character, class, and you put some numbers together using the collect function, it says numeric. So character and numeric we've gone over. Again, integer is just a special case of numeric that can only contains whole numbers. If something's an integer, it doesn't have the number 1.5 in it. Okay? So we've shown the colon operator, 1:5, and that'll give us a sequence from 1 to 5. Sometimes you want to create sequences or, a set of numbers that go in different units than 1. So seq will create those sequences for you. So you say from to, by default, it'll go by 1, right? But you don't have to do that. So if we go from x is 1 to 5, but let's say I wanted to go by 0.25, x will go from 1 to 5 at different sequences of 0.25, right? And so if you do, so the reason we do this, if you run class on this, it'll give you an integer. Just note, it's a numeric vector, just has whole numbers in it. That's all. So again, a lot of times you want to go in indexes of 1, so that's why the colon operator exists. That's why there's a shortcut for it, more or less. Because running seq parentheses 1 comma whatever, usually is so commonly done. You just use a colon. You use the colon operator because it's an operation that's done over and over again, usually on many sequences a lot of times. All right, so logicals we talked about when we do conditions, but again, just like every other data type we talked about, you can collect them together using the C function, right? Trues and falses. It's all caps. It's not in quotes. Okay. So you just write, and you write the whole letter out, the whole word out. Technically, in R, the capital T and the capital F are shortcuts for true and false. Do not use them. Use the whole word true, the whole word false. Why is that? Because I can define a variable named capital T, right? You cannot define something true. Sorry, you cannot define something with the word true. So if I say true equals 5, you'll say, no, can't do that. And by default, just inherently, T is set to true. But T I can reset. Again, technical, but if you see someone's code that says something equals T and they mean true, write the whole letter, the whole word out. Okay? That is what logicals are. You write the whole word true or false out. That's what they are. If you say class, you get logical. So we're gonna go, so now, we showed you this yesterday. There's an is.na function, right? That tests whether something is an NA. There are a whole slew of other is.dot functions. So here, we're saying, let's collect this vector together. It's a character. Is it numeric? It says no, it's not numeric. Is it a character? It says yes. So there's is.numeric, is.character, and generally there are so for every data type, there's an is.character, is.numeric, is.logical, is.integer. And then there's an as function. As.character, as.numeric, as.logical. What that will do you remember when we put both in that previous exercise? We took my.num and my.car, one was numeric, one was a character, and we put them together in the same vector, and it caused it to become a character, right? As will do that. If we said as.character on a numeric vector, on a number, what it will do is say, hey, I'm gonna make this into characters as best I know. I'm pretty much gonna put quotes around the numbers, and then we're gonna treat them as characters going forward. So similarly, there's as.logical, right? So when I talked about coercion, when you want to change the data type of something, you use the as.dot functions. So these are really, really important when you've done something like you've read in a data set. One of the columns has all, let's say again, age. But someone put the word missing in there, right? Rather than put someone's age, they put the word missing. When you read that into R, that column is not going to be numeric. Unless you've been very explicit to say, treat the word missing as completely, as an NA, right? So, if you have, let's say you've done some data cleaning, now you've removed that missing, you turned it to NA. And now you want that whole column to say, hey, these are ages, these are numbers. You would use as.numeric to change the data type of that vector. Does that make sense? So you have a column of ages, you did some data cleaning, you removed the non-numeric data, now you convert it to a numeric using as.numeric. Right? So in Stata, there's dstring, toString, well, there's toString convert, yeah, so toString and dstring, right? So toString is kind of like as.character, right? It makes it into a string, it makes it into a character. Dstring is similar to as.numeric. Okay, so if you see something like this, true, false, but these are in quotes. So what does R think this is? Character. Doesn't matter that it's all true, all capitals, all true and false. To actually turn that into logical, into something where you can do subsetting and all that fun stuff, you say as.logical, and it knows whenever I see all caps true, all caps false, or lowercase, but it's got to be all lowercase or all uppercase. Can't be a combo of the two. Right, so either lowercase true or all uppercase true, uppercase false, that kind of stuff. Again, this shouldn't happen in a lot of the data sets that you're reading in, unless for some reason you have trues, falses, and something else in a data set. So what do you think this is going to come out to be? True. What do you think this is going to come out to be? True. Pretty much as.logical, if you put in a numeric, will take anything that's not 0 and convert it to true. Zeros or falses, right?
Put an even number.
Excuse me?
Let's try an even number.
Negative numbers, true. Anything that's not 0. And again, yes?
What about characters? You just add your characters.
What do you think? Nope. Doesn't know what to do with characters. Even if they're numeric. It says this is a word. Unless it's the word true, unless it's the word false, in all caps or all lowercase, doesn't know what to do. It says, I'm giving up, I'm making it missing. Okay? Yeah, so so we can combine these things, and this is the way you would do this in practice. You take that character, you turn it into a number, and then you can set it to be logical, if you like. Right? So what I'm saying is, usually a lot of times you aren't using as.logical as much. You're using as.numeric or as.character for the most part. And when we get to factors, you'll be using as.character if you want to change a categorical variable in any way. Okay. So logicals, again, you can use sum. What it will do, it treats trues as ones, falses as zeros. If you take the mean, that is the percentage of trues. If you take the sum, that's the sum of the sum. That just takes ones and sums them up. Did you have a question?
I was wondering if there's an as function for an integer.
As that integer, yes. So yeah. Okay. So this is how you can change. This is how you change the data types of columns in your data sets. Right? So dstring, toString, that kind of things. In SAS, I don't know the analogs for that. You can say real. Yeah. Sorry, I don't know that one. So again, and you can use the is functions if you want to check. Just in your code to say, I read in this data set, right? And you can have, we'll talk about if statements, but you say like, is this column a character? Is this column a numeric? If so, fine, keep going. Right, so let's say people are giving you data and it updates. Sometimes if you want to just check, is this a character? Is this a numeric column? And if the answer is no, maybe you want to stop, maybe you want to alert, maybe you want to print out a warning, maybe you want to print out a message, for example, when you run the code, just in case if someone gave you something that was different than the data you got before. Right? So these are just tests to say, is this numeric, is this character? Pretty much what this does, is it runs the class command of sorts, and it sees if it's equal to what you're checking it against. Okay. And again, as that character, you put that on numerics, it'll give you those numbers in quotes. If you say as that numeric, if there's numbers in here, it will convert them. If there's words in there, it's going to treat it as missing. So if we do this, doesn't know how to convert Andrew or Jaffe to a number, but it doesn't know how to convert 1. Okay, so we're going to get into factors now, but pretty much that whole discussion is that when you want to convert data types of columns in your data sets, you'll use like as.numeric to turn it from a character into a numeric. Most of the time though, if there's all numbers in your data sets, and you use read_CSV or read_Excel, it should just convert them to be numbers. But like, as those who've worked with data before, you can not always be sure of that, right? People put spaces in places they might not think they do. People put, words in there. Columns get shifted. Things get changed. New people come in and putting in different things. So data changes all the time. Okay, so now factors is what you do for categorical variables. So it's it's a special character vector where the elements have predefined groups or levels. This is what you think of conceptually as a categorical variable. So the way you convert things to factors is the factor command. So here we're passing in, and you pass in a character vector. So let's say in your data set you have marital status or sex or something else, and it's coded with, words, right? So not 0 or 1. Right? You can keep it as 0 1, and you can convert it later. But let's say, male is the word male, spelled out. Female is the word female spelled out. You just put in that vector into the factor command, and it gives you a factor out. Now, note how it's printed. It's printed as words without quotes. So 1, before you even see that it says levels, you should know that it's not a character vector anymore. It doesn't have quotes. Because these are words, it's not a numeric vector. Okay? So just by the look of it, you should be able to identify that this is something different. The second thing, it gives you the levels. Okay? This is the levels of the factor. First one being the reference category. You can change the reference category, and we'll do that in the next slide. We can give it a different reference, and then later, if you've already created a factor, you can change the reference category later if you'd like. And this is important when you're doing regressions because the interpretability of the coefficients is based on the reference. Yes.
So if you want to use this on a column, you've got 1,000, 10,000 records, you don't really want to see everything first line about what's there. You don't want to have. I want to see the levels so that I know everything's categorized properly. But so is there any way to?
Yep. So 2 things. 1, you could use head, and it'll print out the first 6, and it'll show the levels. Or there's a levels function that'll give you directly the levels out. Right? That says what are the levels of this factor? What are the categories? So if you say class, it's factor by default. If you don't give it any levels, we'll give levels in the next slide. If you do not give it any levels, it will put them in order in alphanumeric order. The only reason boy is first is because B comes before G in the alphabet. So one of the big things that we discussed about read.csv and read_csv, one of the reasons we talked about that, by default, this one, I think the defaults, they thought they were helpful in the sense that whenever you read in a data set, it assumed if you had characters, oh, that's a categorical variable. We want to turn that into a factor. Most times when you're doing analyses, though, that's not what you want. For two reasons. One, you usually want to be very explicit and set the levels yourself. And two, there are a lot of different types of data sets where a column in there, you just want to treat it as words, and you want to be able to do string manipulations. You want to, grab an address or something like that out of it. And you don't want it to be treated as a factor because they don't work necessarily the same way. So, for example, if I put in a column here that had addresses, right, and I didn't specify the levels, every single unique address would be a level of that factor. That's not very helpful or efficient, right? Categorical variables, this is super helpful. Something where you have something unique to every single person, every single record, you want to keep that as a string. Okay, read underscore CSV does not do this by default. It will not change your stuff into factors. You have to do that on your own. That's why the factors command is here. So, most important things, I would say, obviously X, the thing you put in there, and second, the levels you specify. Now, if you specify a level, so let's say you have, in this case, you had boy, girl, and other in this vector. But in levels, right, it'd be like boy, girl, dog or something like that. Right? You had a dog in there, right? So levels, for example, you specify the only levels that I accept are boy and girl. The variable, the record that is in dog, that has dog in there, that will be treated as missing because you didn't say that was an acceptable level. Okay? Sorry, that being said, one nice thing about factors, when you do a crosstab, it will do a printout of every single level. So let's say you did boy, girl, and this was your vector, but your levels was boy, girl, and dog. And you run table. By default, dog will have a column, it'll just be 0. Right? So sometimes you want to enforce that you always get out all these levels in your table. Right? Even if that data doesn't exist. Even if that data isn't seen, even if that record, that type isn't seen in your data set. Just for standardization. So levels are really helpful. You can make ordered factors. I generally don't do that. There are very specific cases where that's important, but when you want to do comparisons. But anyway, we generally do. These are the big two: character, levels.
I have a question. So
Yeah.
with this, you're not forcing the levels. You're telling it to take the levels from what's already in there.
If you do not enforce the levels, it'll take the unique elements of that vector and then call out the levels and then order them alphanumerically. Okay. So here's an example. So let me, the way to specify levels is in the factor command. That is the take-home message of this slide. And if you want to extract and find out what the levels are, the levels function is fine to do that, but you do not set the levels of a factor with the levels command. It is dangerous. And I'll show you exactly what I mean. So if I say level CC, case and control. If I want control to be I want the reference to be control, that's the way I do it. I put the levels inside the factor command. Okay? The levels function will tell me what are the levels. More or less, whatever you see here will come out right here. Okay? So if you want to see what a factor's levels are, use the levels command. Now, here we did case control. Again, why is case first? Because case comes before control in the alphabet. We didn't specify the levels explicitly. Now, we can reset it using the levels function, and some code out there will show you to do that. But it is bad. It can cause some problems. It can cause complete flipping of your labels. You don't want that. So what we did right here, level CC equals control case. This does not do what you think it does. So note, the very first record is a case, right? The very first record down here is what? It says control. So this does not do what I just showed you. It does not order the levels correctly. It sets them in a way where it says, oh, yours is control and case, so everything that says case should now be control. Everything that was control should be now case. That's not what you normally want to do. So again, the way you do it specifically, or the way you do it correctly, is you specify the levels within the factor command. It doesn't, so this is a character vector, okay? Cases and controls. If that was already a factor, it's okay. It'll still make another factor. It'll make a factor with the levels correctly. And what I mean by that is let's make this. Right? So let me let me call case control this. Sorry, let me just bring it up to the top. So control is our baseline category. Cases are not. All right. So is everybody clear about this command up here? Just putting factor in. In this case, I'm just putting a character vector. It could have been a column in your data set, and I'm specifying the levels directly. Now, you can pass in a character vector, or you can pass in a factor that's already defined, and you're just redefining the levels here. The data is still case, 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 control, 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 case, 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 control, control, control. Just the levels have flipped because I explicitly redefined them. So I'm saying, even if you have a data set that already has a factor, you can still use the factor command on that object and reset the levels. But you don't use the levels function. Okay? And again, you can also do ordered equals true. That's not really, the only times you may want to do that is in terms of like something that's in terms of severity. But a lot of times you're not using ordered factors. And you'll see that it says like control is less than case. So the only reason you do that is if you want to use compare operators, like x is greater than control or something like that. You could do that in this case, but a lot of times that's not the way you subset data. All right, so we have that factor back, right? Control and case, controls our baseline. We say as that character, it gives us the data back as a character string, okay? If you have a factor out there and you say, I want to do some string manipulation or something like that to it, you should be doing string manipulations on a character, you use as that character, okay? You can do as that numeric on a factor. What that will do, sorry, so what is the baseline category here? Control. Yeah, the reference category, baseline category, yeah, control. And case is the next one. There could be 5 or 10 levels, it doesn't matter. In this case, we only have 2. If you do as that numeric on a factor, it will take, so remember the first record is case. You say as that numeric, it'll give you the index for the level. Usually never do this. Yes?
How do we compare factor variables? Like, I want to plot only the case file, cases.
So you can still do filter. You can still filter on a factor with equals quote case, for example. So what I mean by that,
Using quotes.
using the same way you would do it with a character. Okay.
Would it work if I try to like compare it to 1 or 2?
I don't know. No. So what it'll do is it'll treat it as a character, right? That's like saying this, right? If you wanted to say is the first level, for example, you have to change it to a numeric, right? But again, so why is this important, or why do I think this is great? So in other languages, for example, in Stata, a lot of times you might have to remember the reference category. Equals equals 1 equals equals 2. Sometimes you can do it with strings. But here, you do things much more explicitly. You say, what is equal to a case? You don't have to remember if the factor is, if this is the reference category, this is the reference category, right? You just operate on the factor that says, like, I want to get the cases, I want to get the controls. I do not care how they are, which level is which. I want to filter the data on cases, for example, and plot only those. I want to filter on controls and plot only those. And so you can do that just like a regular character string, but on top of that, when we go to modeling and tabling, it will do the correct things in the sense. When you use this as a factor in a model, it will create the reference category as the 0 category, indicators for every other one. Okay? All right. Why am I not? All right. Yes.
The previous example before that.
Mhm.
There was one where you had done something about excluding the ones that are missing.
The help file for factor. This?
Right. So what if you didn't want to exclude them, but you wanted to remove those as missing?
So, good question. So you should, if they're NAs, right? Or, okay, so there's two separate questions. Let's say they are already NAs, they're missing. And you wanted a level for missing. That's one question. So what I would do is I would change those characters, right? I already have that. I can use the is.na function. Right? We'll talk about how, get, subset on NAs and replace them. We just did that, right? We said something equal to 0, replace the NA. So what I would do is replace those NAs with a character that says missing, and then set the levels explicitly. But alternatively, if I had a character vector that said like boy, girl, dog, cat, whatever, there's you would change those strings to missing. So let me show you what I mean. So let's say X is boy, girl, cat, dog. And I want to factor X levels boy, girl. So that doesn't work. That doesn't work, right? Exclude doesn't do. I think what you're asking. What I would do is say like X equals, let's say, dog is missing. I would change the vector. I would change the vector itself, right? Say factor X. So I changed dog to missing. So we're going to talk about percent and percent in a second. But let's say I had a whole set of other things, right, other than boy and girl. But they weren't NAs. I would say X, is it in this list? I would just set that to missing and then make the factor. Does that make sense? Alternatively, right, let's say we had a missing value. I would say, give me the ones that are missing and replace all of them with the word missing. And then I would make a factor with a level that said missing. Okay? I mean, so that's being explicit. That's also That will kind of circumvent the problem of tabling, right? So tabling, there won't be any missing values by the way we did it. So all tables will have a category missing. Does that make sense? Right. So there's going to be no more NAs in that. That's a good question though. Again, we're not using levels. All right. So before we go on, so factors are super important, right? They're pretty much how you work with any categorical data in R. So the nice thing about them is that you can still work with them like they're strings. They work with all the kind of functions that work with characters and plotting and stuff, things like that. So I'll show you after we're done this lecture, like what happens when you go to plot some y variable against a factor, what happens. And then you can convert back and forth from characters and factors using as dot whatever. Using as dot character. So this is different than other software packages. So you don't have to remember necessarily the levels. You just have to remember what it's labeled. Right? But like everything else in R, if I said, so let's get off this. If I said this with a capital C, right? Everything that was a case would be missing. It has to be explicit. It's a case specific thing, right? You can't put something in here. It has to match exactly. That is really important because if you've ever gotten data, I use the sex variable as an example a lot because I've gotten cases where male is lowercase, uppercase, misspelled, just M, just F, capital M, lowercase e, capital M, lowercase ale, right, for female, right? So we have to do string manipulations. We have to do some cleaning in order to get that into this. But just off the bat, if you said male and female, you wouldn't get the things you want. You would get missing. But that is kind of good because if you get missings, then you can identify the cases where stuff became missing, and you can go back and see what happened, what went wrong. All right, so some other functions that are sometimes helpful, utilities. So rep is a repeater. Repeat this thing. So in this case, we're going to repeat boy, girl, each. So rep has two different ways of repeating things, each of them 50 times. So this will give us a vector back length 100. So it'll be 100 things. The first 50 will be boy. The next 50 will be girl. Okay. If you say rep boy, girl times equals 50, that will still give us a vector of length 100. Except instead of going 50 boy, 50 girl, it'll go boy, girl, boy, girl, boy, girl, boy, girl, boy, girl, 50 times. Okay? Sometimes you want one, sometimes you want the other. They're both 100. Okay? So, a lot of times when you're creating categorical variables out of continuous variables, we'll use this function called if-else. So, it returns a value with the same shape as test, which is some of these help files are very not as intuitive, which is filled with the elements selected from either yes or no, depending on whether the test is true or false. So pretty much what you got to do is if else, you put some logical tests in here. Something that comes up true or false. Okay? And then if it's true, it'll replace it with this variable. If it's no, it'll replace it with this variable. Sorry, value. And let's demonstrate that. So we're back to this, x. So let's put another missing there. If else, is that NA x? Right? Let me go back up to the top. So here's one way to replace missing values with something. So, if else, we put in a logical vector in there. Is it NA, yes or no? Okay. True values will then be converted to the word missing in all caps. Anything that's not missing, we're just going to put the value of x back in there. We're not going to change that at all. For things that are false, we're not going to change anything about it. Okay? Does this make sense? So if a test What happens if the test is true? What do you want to replace it with? If the test is false, in this case, we want to just keep it as is. We could have also we could have made it something else. Right? Doesn't have to be that same variable put in there. Okay? So we're going to read in the circulator data set again. So here, we're going to create a new variable that records whether daily ridership of the circulator was above 10,000. So we're going to create a new variable, not a new column in the data set. We're going to say if else daily is greater than 10,000. If it's greater than 10,000, call it high. If it's lower than 10,000, call it low. If it's equal to 10,000, it will be called low. Then we can create, we can turn that into a factor, for example, and say the levels are low, then high. Again, if I don't specify the levels, what are the levels going to be? Alphanumerical, so we go high and low. Usually that's not what we want. So we explicitly say low then high. Again, we see here, low, high, low is the first level. We do a table, just go across after that. So you can do tables on factors, all that stuff is good. If we put another level in here, it would have another column, and that would just be 0. So this is the way, I just selected a few columns out of here. But this is what, so if else works really well with mutate. Right, so we have this data set. We want to mutate, we want to create a new column called high rider. If else, the daily ridership is greater than 10,000. If it is, high, low, and then I just use select so we didn't print out all the columns. Yes?
Can you nest like an if else inside another if else?
Yes.
Oh, it's just
Yes.
Sorry.
So we'll get to that. But is this clear? So mutate, redefining a variable, right?
But is there a way to like you want to do several? Like, is there an easier way?
Yes. We'll get to there is. We'll get to that in about 2 slides. So let's say we can do the same thing we did before. So okay, before I go through, this is clear. So we're saying if daily, remember it's in the dplyr function. It knows we're trying to grab one of the columns of the data set. It's greater than 10,000, call it high, otherwise call it low. Let me okay. So let's say the daily ridership is over 10,000. Let me take all this out. Oops. Another parenthesis. So let me do 1,000 to demonstrate this. Just like we did with X, where we said, it's not there. You take this data set, create high rider, that says if it's greater than 1,000, just set it to be 1,000. Truncate the very top end. Right? Anything above that, let's say you had blood pressure or something like that, or heart rate or something, and it was below, let's say 0. Right? You got something really strange. You want to set that to 0 or something like that. Or you got something below a limit of detection, right? And you wanted to set it to that limit of detection. This would be the way you could do it. If it's greater than 1,000, set it to be 1,000. Otherwise, just keep the variable as is. Okay? I think that's a good example. I think that's a dangerous thing to do with your data. Just be sure you know what you're doing. Right? So you can nest these. It's sometimes not the most intuitive. Right? So, for example, this is what we're going to do. We're going to create three levels. 0 to 10,000, 10,000, 1 to whatever, 20,000, and above 20,000. We're going to call high, medium, and low. So we can nest them. If else, cert daily is less than 1,000, call it low. Otherwise, go to this condition. And it's going to say if it's greater than 20,000, call it high. So if you failed on this and this, if you've gotten false for both these, right? You're not less than 10,000. You're not greater than 20,000. You're between 10,000 and 20,000. So we're going to call that one medium. Okay? So you can nest these. We're going to talk about maybe a more intuitive way in a second called cut, how to cut things based on certain breakpoints. But this is important because sometimes you're not cutting things at breakpoints. Sometimes you do want a series of if statements or something like that. You could have broken this up into two separate conditions. You could say if circ daily is less than 10,000 low, and then you could have called it high, and on the next line you could have used this if else statement again. Okay? And what I mean by that, I'm going to run this command just to show you. Table rider levels, right? We got low, medium, high. What I'm saying is rider levels. We could have said if it's less than 10,000, call it low, otherwise it's missing. Sorry. Oh, that's wrong. Sorry, I screwed that up. I'll make it again. So there are ways to do these in two steps. I usually don't do it this way, so that's why I'm a little bit confused. But you can nest them. It's not the worst way to do things, but it's not always that clear to do it. But in order to do something like this where you're based on cut points, we're going to talk about the cut function. So let's say you have a continuous vector, and you would cut it at certain breakpoints and make factors out of it. Like low, medium, and high, quantiles, quintiles, that kind of thing, deciles. Cut function is very useful for that. So what you do is you give it a vector, x, you put in the breaks, and you can make the labels for those breaks. Okay? So cut divides the range of x into intervals and codes them to x according to which interval they fall. The leftmost interval corresponds to level 1, the next leftmost level 2, and so on. So I will say one thing. The default here is not that great. So what it will do, it will take x and the breaks that you give it and break it up. And I mean that the default's not great is because the include.lowest equals false is not always the best thing. Because let's say a thing goes from 0 to 10, and 0 being the minimum, 10 being the maximum. So if you put the breaks, so it'll break at 0, anything that is equal to 0, it will return as missing, which is not what you want. So let me show you. So yeah, let's go over these a little bit more. So numeric vector, either a numeric vector of 2 or more unique cut points or a single number giving the number of intervals. So you can say breaks equals 10, and it'll break it up into 10 different what's it called? Intervals. Right? Say I want 10 breaks, I want 4 breaks, stuff like that. So let's do, I'm going to create a random normal, a random number, let's say cut x breaks equals 10. We'll do the head of that so we don't print it all out. So it makes 10 breaks, right? Levels, so forth, right? And so the way you read this is the way you read, I'm going to clear this out and just bring it to the top again. The way you read this is the same way they do in like mathematical notation and stuff. So a parenthesis means it doesn't include this value, right? So 2.49, negative 2.49 is not included in this level. Bracket means it is. Negative 2 is included in this level. So what I mean by that, negative 2 is included in this one, not this one. Okay? So where you go to the edges, it just matters how you include it or not. Does that make sense? So just like the intervals and the interval line that I think most of us learned in, I don't know what year, but the interval line on the left, the parentheses means up into that point but not including it. The right bracket means up into that point and including that point. So the right one, the very last one, should always include the maximum. Right? So 2.38 was the max. The reason I say I think this is a bad default is because the very, very minimum point, by definition, when you say include dot lowest, and I mean lowest is the minimum, it is false. If your value is equal to 2.49, negative 2.49, it was coded as missing up here. So you have to set this to be true to make sure this very first category includes your lowest value, which a lot of times, for example, includes 0, which you might have a lot of cases of. Note, this is not how you make deciles. Right? It makes more or less 10 equally spaced categories. Okay? So it takes the max minus the min, divides by 10. That's how big your intervals are, and we'll make them. All right, so 2.38 minus negative 2.49 divided by 10. You'll see that the width of each interval is around 4.487. Right? That's how it determines it. It's not based on quantiles or anything like that. I'll show you how to do that though. Okay. Okay, so here we're going to give the breaks. So okay, we're going to use cut. We're going to use the daily ridership again. Okay? What are the breaks? And we're not going to give it, we don't want 4 breaks. We want specific breaks that we define. So you say break 1 is the minimum. And we're just taking the minimum value. That's the one we want to say is the start of our breaks. Up to 10,000. 10,000 to 20,000 will be an interval. 20,000 to the maximum is our other break. So again, there are 4 breakpoints. That means there are 3 levels. Okay? Minimum to 10,000, 10,000 to 20,000, 20,000 and above. Right? 4 breakpoints define 3 intervals. Okay? Labels. Labels now, we don't want it to have this syntax. We don't necessarily want it to be like 0 to 10,000, 10,000 to 20,000, 20,000 to whatever the maximum is. We want them to be labeled what we want them to be labeled to be. So we can pass in the labels into cut. Say low, medium, and high. So the first factor is going to be low, the second one's going to be high, and then again we have to use include.lowest equal true. Otherwise, anything that is equal to the minimum is going to be treated as missing, which is not the behavior we want. Okay. But cut is really nice because a lot of times you want to make some sort of breakpoints to see kind of maybe linearity of some continuous variable and something like that. All right, and then when we couple cut with the quantile function to get those breakpoints, right? Then we can start making deciles, quantiles, quartiles, and so forth. Okay. So again, if we do table or if we do head, we see low, medium, and high. And just to be clear, so we're doing a two-way table here. So we did X is riders labels 2, Y is riders levels 2, rider levels. Riders level 2 is the one we made with cut. This is the one we made with the nested if statements. And all this is showing, everything's along the diagonal, they're exactly the same. All we're showing is that they give you the exact same answer with respect to the levels, right? So again, cut will give you factors back, right? We do cuts. We say 0, 10, 25, 100. X, we're just giving numbers from 1 to 100. CX is the cut X. And we see we gave 5 breaks. We got 4 intervals back. If we do tables on that, we get those. But again, it's not giving us the quantiles. It's just giving us, if we give it the number of breaks, it's not giving us anything with respect to percentiles. It's just giving us evenly spaced breaks, evenly spaced things. So if you say labels equals false, it just gives you a numeric vector back saying what level's it in, right? So 1 being first level, 2 being second level, 3 being third level, 4 being fourth level. So if you really, for example, want to do deciles and you want to know which deciles is this in, and you don't want it to be labeled like this, you can do it where you say labels equals false, and level 1 will be first decile, second decile, third decile, all the way to 10. So, really quickly, remember, x is 1 to 100 in this example. If you put data in there but don't specify the breaks in a way that data can fall outside of these breaks, right? So here, 10, 25, and 50, the only data that's going to be recoded is data between 10 and 25 and 25 and 50. Anything that outside of that range is not going to be coded. It's going to be missing. Right? So remember, this is x is 1, 2, 3, 4, 5, 6. All those don't fall in this range, so it'll be coded as missing. So that's why it's important to do the minimum and the maximum if you're working with data. But sometimes if you do want things, if you only want to do breakpoints within this range, you can do it that way. And again, we're just tabling that up to say the 2 levels we got for data between 10 and 25, 25 and 50. Everything else is NA. We had to use the if any on the table so that we could actually see the missing. Okay. So what? Plot margin is too large. So I have to. Let me make. Give me one sec. 1,000 R normals. I'm gonna make it bigger in a second. Okay. So I just got some random normal data here. But let's say I want to cut it based on quantiles or deciles. So do people use deciles a lot? I don't know. I feel like in the epi class they showed deciles a lot. Maybe not. Let's do quantiles. That's definitely something. So the nice thing about quantile by default, so I'm just going to assign it to be Q, 0, 25, 50, 75, 100. If I put these in as breaks, how many intervals will we have? It's going to be 4, right? 5 breaks, 4 quantiles, or 4 intervals. So let's cut X, breaks equals Q, right? I'm going to call it QX. So by default, we should have evenly spaced data, but again, we're missing one because the minimum's not in there. So we say include. Oh, table it, right? So now we have 250 in quartile 1, quartile 2, quartile 3, quartile 4. They should be even. They're quartiles. That's the whole definition of them. Okay, so yeah, so that's one way. So you can create the quantiles or whatever probability breakdowns you want, right? I could have done probs equals, so seek 0 to 1 by 0.1, and all of the deciles. And then let's do this. I'll have the data broken up into deciles. If I don't want those labels on there, I just want to know if I didn't want to put, again, I said labels equals false, so it didn't give me those labeled factors here. It gives me a numeric vector, so I know I could say like x equals, or qx equals 6, and I know that's in the 6th decile. Okay. All right. Great. So again, characters are important. Use them for a lot of string manipulation. When you want to actually use them for analysis or usually for reporting, you usually convert them into factors. Right? Factors are where you do your modeling, your analysis, that kind of stuff. But usually you want to be explicit about making the levels. Cut is a very helpful function when you want to make a factor breakdown. Usually a lot of times it's very powerful when you couple that with quantile or something like that that estimates things where you want the breaks. So now, dates. The bane of my existence. Dates. So, dates are really important. They're in almost every data set, and they are usually a nightmare to deal with for many, many reasons. One example I had from a study we were on, I asked for about a year to have clinicians use a drop-down calendar. They click the buttons. They said, no, that takes too long, too much time. Let's have them write in the dates with slashes. It would be slashes, it would be dashes. And so finally, we had some European sites come on, and luckily they had an enrollment around June. It was around June 5th, which is fantastic. And their follow-up was a month later. Or sorry, their enrollment was in May, and they had a follow-up about a month later. And I asked our database manager, I said, tell me what this date is. Is it June 5th or is it May 6th? If you can't answer that question, give me the calendar. We got a calendar, hopefully about the next month implemented in the system. So that being said, dates can be encoded in almost infinite different ways. And then it's also much more complicated when you're not just talking about dates, you're talking about dates with times. But luckily, there are some really good packages in R to help you deal with that. So when we read in the data set, it didn't say, hey, these are dates, I'm going to convert it to dates. We're going to do that on our own. So again, we see this, it's character, it's got quotes around it. So there is an as.date function, which will convert things to a date. And you have to specify the format. So the function goes as.date, the date variable, and you say %m for month, %d for day, %capital Y for 4 years, %little y if it's 2 years. This is the way you'll see online, you'll see dates conversions. It's good. It'll convert it to a date. You'll see there's still quotes in here, but the class has now changed. It's now a date. If we do range, we see that it's the range of the data, the range of these dates is ordered. It knows what if one date is later than the other. We're not going to, so I don't recommend using as.date anymore. So there's a package, not surprisingly by our studio, that is called Lubridate, right? So they like to make fun little names for their packages. So it's supposed to make working with dates, I guess, more fluid, more easy, right? It's supposed to get some DW40 in your dates. WD40, DW40, what am I saying? Okay, so the functions they use are pretty explicit, but they're way more intuitive, and they're a lot smarter at guessing. So if back here I said /m/d/y, and you didn't have a 4-year, year, it's going to come as missing. It's going to say, didn't know how to convert it, but it's not even going to give you a warning necessarily. In Lubridate, there are functions for almost every single format. MDY says the data is month, day, year. Okay? And you just put the date variable in there, and that's what you get out. There is a DMY, right? There is an MDY_HM for hours, minutes. There is an MDY_HMS for hours, minutes, seconds. Right? So however your data is formatted, there should be an associated function that matches that. Now, sadly, if there's so much mixing and matching that that it's formatted in 5 different ways, you still have to do some data cleaning. It's not magic. You still have to work with your data. But again, if we do MDY, we get the exact same thing out that we had before. 2010, the range is still the same. Gives you the range of the dates. Okay. So if I say, let's go back to as.date. Circ date %m, %n. You don't have to remember all these fun things like percents. If you say the class of that, it says it's a date. Dates are fine, but they generally only refer to like a day. And I don't mean like if there's times, it's not a great, it doesn't hold that very well. There is a different class called POSIX-CT. Again, not that important. Just when you say class, after you run some of these date commands in Lubridate, if you say class and you see this thing out, POSIX-CT, POSIX-T, all that means is it's a time. It's a date time format. That's all. Your data is encoded as a date. Okay. The Lubridate function also has really helpful things, or a really helpful function called as.period. So let's say you want to add 20 minutes to your date object. So in this case, I just took the time, like the time I ran this, right? And I say as.period 20 minutes. I want to add 20 minutes to right now. So let's say we ran this at today at 12:19. Add 20 minutes, 12:39. So for example, let's say visit 1 is in June. You want to add 1 month, right? So you want to know what is the date for this person's next follow-up. Let's say I want to, look at all the data all the visits that have follow-up, and then I want to create, visit records for people who don't have it. You can add to that, right? Or let's say you have data that's supposed to be measured every 5 minutes. You can say as.period, put a vector of 0, 5, 10, 15, 20, 25, 30, so forth. And you can say, do we have all those records? Yes or no. Right? So it allows you to add or subtract things to dates by specifying how long and the unit. So usually, a lot of times with dates, you care about the first or the last. Right? So we talked about data where you have, let's say, multiple records per patient. And you have, or per person, and you have dates for those. A lot of times you want to say, what is the first date? Right, what is the first one? So you can say, like, days from baseline, minutes from baseline, right? So there are first, last, and nth. These are functions in dplyr. First gives you the first, last gives you the last. Nth, you can specify which one you want to give, or which one you want to grab. So I'm already going to assume that the data has been sorted, right? It matters the way they're sorted, right? So I'm saying first won't automatically give you the lowest date. It'll give you the first record. Let's say if we were going by patient ID, and let's say they weren't sorted, it's going to break out the data by patient and grab the first record, okay? It's not, you have to have explicitly arranged the data by patient ID, then date, then do the extraction. Does that make sense? So I'm getting some confused. So like, let's say I have five follow-up visits, but the way in the data set it is, today is one of them. Yesterday is another. Yesterday I had a follow-up visit, right? The day before I had a follow-up visit. But it just so happens the way the database is set up in the actual spreadsheet. Yesterday's visit was the first record for me. So if I didn't sort the data explicitly by ID and then date, that first record for me is going to be yesterday's, even though my first one could have been way back when. So I have to explicitly sort ID and then sort on the date so that if I want to extract the very first record, I know that's the first date. This data set is already sorted. So I just want to be clear. So if you do in Stata, right, the lowercase n, little n equals 1 is first, big N, or little n underscore n is equal to underscore big N is last, right, using bisorts and all that fun stuff. So little n underscore n equals 3. So okay, so we take the data, mutate it. I want to say the first date is equal to this date vector. Remember, we went back. We created this to an actual date format. So I want to say the first date is equal to the first record. The second date, or the last date, is equal to the last record. The third date is equal to the third. Again, not too interesting, right? All it does is grab the first, last, and the third out of this entire data set and repeats that over and over and over for every record. Maybe useful, maybe not. right? I could have just done min, max, and sorted it. Yeah.
Can you do it by ID?
So here we're going to do it by day. I mean, day of the week. So we group it first, right? So in this case, exactly. If we're doing this with patient data, you would group it by patient if you wanted to do it that way, or site, or whatever you wanted to group it by. And then you can grab first, last. And so you see here, the first Monday was the 11th of January in 2010. The last Monday was the 25th of February 2013. The third Monday was the 25th. The third Tuesday was the 26th of 2010. Okay? So it grouped it, so in this case, before, understandable, not too interesting, repeats the same thing over and over again. Here, when you group it by something, that's where this stuff comes actually really useful. The first and the last is when you can grab records based on index or based on some other sorting if you've done arranging beforehand. Okay? So, for example, this could be like baseline visit or something like that. And then the lovely thing about dates, you can take the date and subtract this off and give it in some sort of units if you want like days from baseline, hours since baseline, months since baseline, or whatever. So that's what we're doing here. So we grouped it by day, we grabbed the first date, and then we're doing a thing, so we're taking a difference in time, a diff time. So the syntax for this is unintuitive to me in the sense that I always think of time 2 minus time 1. Right? That's the way I think. In diff time, which will take differences on dates, for some reason, it's time 1 minus time 2. Okay? So what this will do, I mean, you should be able to see that immediately if you've done something wrong because the times will be negative. Right? If you haven't done it the way you want it to be. So you say, okay, take time 2 or time 1 to be the date, time 1 is new date, all the date values. Time 2 is the first date. So all I'm saying is for every single day, subtract from the very first date. Right? So this is kind of time from baseline, except in this case we're using days. Right? If it was patients, it'd be time from baseline for each person. So let's look at it. It says the time difference in seconds. This gets printed out, and it says 0, 0, a whole bunch. Right? We usually don't want that in seconds. So what you can do is use the units command to change whatever units you want. Days, months, years, seconds, and so forth. And so then they'll be stored as time in days. So in this case, it's 0 to 7 days versus using time in seconds, which isn't very useful. Then things like this, you can change it to a numeric. You can change it to an actual number if you want. You can still plot these things, that kind of stuff. But pretty much break it down three things. One, Lubridate has a lot of functions, and I'll go into them very briefly, that allow you to work with dates very easily. Diff time allows you to take differences in dates. The units for diff time can be changed so that they are intuitive to what makes sense. Sometimes hours make sense, sometimes minutes make sense, sometimes days make sense, sometimes months make sense.
And is it part of the Lubridate package that it recognizes what days are? Or is that something you set?
That is for Lubridate. Yes. That might be base, but I'm not. Yes, sorry. In base, you can assign. It's when you load up R, right? So it's saying if you have an object that is a difference in time, you can change the units. These are the acceptable units, right? You can't do like bi weeks or something like that, right? That doesn't make sense. That is not something that's implemented. Right? So again, we talked about data frames at length, right? We can have different classes. Matrices are kind of specific. We didn't go into them before because when you load in data, they're not going to be in a matrix format. You can convert them into a matrix format, but again, like vectors, matrices have to have one specific data type, all numerics, all characters, all logicals. And we're going to show you just brief things if you encounter them in the wild. This is how you deal with them. So we're going to just create a numbers 1 to 9. So in order to create a matrix, it's the matrix command. you pass in the vector, and you tell how many rows and how many columns it has, and then it fills it in by default by column. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, we've talked about these: n row, n col names, row names. So n row, the number of rows; n col, the number of columns, right? In order to count things. That works on data frames. It also works on matrices. Dim also works on matrices, right? Col names works on matrices, but as you know, by default, it's not given any column names, but you can set them to be something. The big difference is matrices cannot be subset, even if they have column names with the $sign. That does not work with this. Second, dplyr functions don't work with matrices. You have to convert them to data frames. It's simple to do, but it's good to note if it says this is in a data frame, you're like, why not? It could potentially be a matrix. Also, really briefly, the way it's printed out looks different. The columns are set to be things like this. When you print out a data frame, it doesn't look like that. It usually have column names, or if it doesn't have a column name, it would be NA or something else up there. So you use bracket subsetting for matrices. Okay? Like we did before, 1, 1, give me the first row, first column. 1, give me the first row, all the columns. 1, give me the first column, all the rows. So again, bracket notation. If these were named with row names or column names, you could put the column name in here, for example. And again, you could pass in the vector of column names or a vector of indices for which columns you want to grab. Note though, if you grab only one thing, if you grab one row or one column, it's not a matrix anymore. It grabs a vector. Okay? If you grab more than one, it's still a matrix. There are ways to make sure that it always returns a matrix, but for the most part, just note that if you grab only one thing off, it's going to give you a vector back. A lot of times that's what you want. Sometimes you don't. So there is a function. So we've talked about data frames and tables. There are other two-dimensional things. They're like matrices. Each column is a vector, but it can have its own class. Matrices are all the same, either characters, numeric, or logicals. But if you want to take a matrix and convert it into a data frame, we see that class Matt, see that it's a matrix, right? What were the functions we used before? What if I wanted to change a character into numeric? What did I use? As dot numeric. As dot data dot frame converts a matrix or whatever this thing is into a data frame. Okay. Now, most of the time if you're working numeric stuff, all good. You see that it prints out differently. Look at the rows and columns. You got brackets and stuff up here. That's how matrices are printed. Data frames aren't printed that way. So again, there are certain cues that indicate what classes are while you're using them. Lastly, let's say, okay. Can be characters, it's all fine. The one thing I will say though, if you use as.dataframe, still works. But, one caveat. This by default will assume that if you're passing in strings, to convert them as factors. So if I do df $v1, it is a factor. Right? Sorry, let me make this bigger. It is a factor. The option to make that not happen, strings as factors equals false. So, statisticians are, a wild bunch, right? Obviously. So at some of our conferences, there will be member badges and things like that. A certain contingent of the staff community who uses R very frequently have badges that say strings as factors equals no, with some expletives, let's say, on there, right? That is given. So this is a thing that a lot of people who've worked with the language a long time, or some of the time, don't really like, because it's not a behavior that you usually want. You usually want to work with the strings, make things explicitly factors yourself. So if you're converting using as.dataframe, just always be sure to say strings as factors equals false. Again, this is a great reason why you use RStudio. I can write strings, hit tab, it'll complete this. This is a fine argument. It is a very explicit argument name, strings as factors, but it is long to type out. Also, it's camel case, right? Camel case being, that's what they call this when you have lowercase things, and when you break up to another word, it's uppercase and then uppercase. So that's one way. You can define variables or arguments that'll be human readable or readable rather than something like. That's even worse. That's impossible to read, right? In some respects, strings as factors, just without any camel case. But a lot of times people do something like this. But still, that's a super long argument name. So without being able to hit tab and complete it, it's kind of a chore. Okay. I'm going to run through lists really briefly. Okay. Lists are like generic, or like just general containers in R. It contain anything, right? So the way you make a list is the function list, right? So they can hold anything in their elements. Vectors, characters, strings, matrices, data frames, other lists inside of them. They're kind of like those Russian dolls. You get a list and a list and a list and a list, right? So you can reference it. If it's named, you can still use dollar signs to grab it, similarly to data frames. But the weird thing is, or the difference is, if they are not named, if you want to grab something by the specific index, you have to use this double bracket notation. Right? So, okay, I'm going to make a list using the list command. The letters, A, B, C, right, capital A. Numbers is 1 to 3. Matrix is 1 to 25. So this is a list with 3 elements. The first element is a character vector. The second element is a numeric vector. The third element is a matrix. That's 5 by 5. Okay? So the first 2 are named. The third one is not. This is how it will look like. You'll see this double bracket notation. If you wanted to get the third element, you would say my list, bracket, bracket, 3, bracket, bracket. And that'll extract this matrix. Okay? Yeah. So some things these are really useful for. Sometimes, let's say you have a data frame, a model in there, maybe a second model, and like a table. You can have that all combined into one big object so you can kind of manage that together. Or let's say it's a list where model 1 or element 1 is the model for cases, element 2 is the model for controls, right? And it could be labeled like case, control, and you have both models separated, right? They're not together, and you can reference them relatively easily. The thing is, though, you can use single brackets. The issue with that is this doesn't extract the actual elements in there. What you see is here, my list bracket 1 returns something with a dollar sign, right? It looks still like this, right? It just deleted these 2 things. That is because if you use single brackets, it returns a list, right? If you use double brackets, it'll return the actual elements in that list. Again, this is confusing, obtuse, but sometimes some of the functions you use may return a list, right? So if you want to extract the things out of there, you can use the double bracket notation, or you can use the dollar sign if they are named. And you can, if you use the double bracket notation, you can use indexing based on numbers, indexing based on a name, or indexing with the dollar sign. But again, if you use single bracket notation, you can select multiple elements of that list, but it will return a list still. It won't do anything to the data. Yeah, so for example here, we're grabbing the second element. Remember, it was just that numeric vector. Let me go back really quickly. The second thing is numbers, 1, 2, 3. That's the second element of this list. If we do this, it's going to say, grab those numbers and grab the very first element out of that vector, and that number is 1. Right? Here, we grab the third thing, which was that matrix, and we grab the first 2 rows and the first 2 columns. So this is a way where you can, instead of reassigning, you can drill down into the list and then extract things out of there. But again, we're not going to use them that frequently. They're not that widely used, I would say, in some respects for new users because you're just working with a data set or two, but they are very useful in the long run. Okay, so I'm going to do about probably like 15 minutes and then maybe take like a 5-10 minute break. Unless you want to take a break now, or no one's really adamant about jumping out, but in 15 minutes I'll probably take a break, take a little breather from talking so I can answer some more questions. But before we do move on, questions. So again, yes.
So you put up a couple weeks to drill down on the list. Can you use $2 signs, or is that not?
You can.
Okay.
If that element that you grabbed allows you to grab it. Yeah. So like, let's say one of them is a data frame.
That's exactly it. So I'm thinking about a list that has a bunch of stuff, potentially 2 or 3 data frames, maybe part of the same data set, but different cohorts.
Exactly. Yes.
Okay. Cool.
Good question. So again, recap. There's is dot functions, as dot functions. Is dot functions will give you logicals or trues or false, whether something is a type of object or not. As dot functions will coerce them into whatever you want them to be. That being said, R is not magic. If you try to coerce a character into a number, into a numeric, and you have a bunch of words in there, it's going to say that's missing. I don't know how to encode that. Is.NA is the way that you check for missing data. You do not use something greater than NA, equals NA, anything like that. Okay? All right. So data cleaning, investigating your data for inaccuracies, recoding in a way that makes sense and more manageable. Look at your data. Look at your data until you get sick of looking at your data, right? And you've done a thesis, like that's kind of the point of a thesis is kind of one person looks at a data set for like so long they get sick of looking at it over and over again in some respects. Right? But looking again, you can see patterns. And I don't mean, staring at a spreadsheet over and over again. I'm saying exploring it with box plots, other things like that. So, is.NA, super, super important. The negation, right? You'll use that a lot. There is no function that is not NA, right? There's no function that does that. You say is.NA, and then you negate it. That's the order of operations. So I want to subset on NAs. I say is.NA, and I can put that in brackets. If I want not the NAs, the non-missing data, use the not. Okay? But it's not is not NA. Something like that. So there's some other helpers. All takes in a logical vector and will be true if all of them are true. So let's say all is.NAS. Is everything not missing in this column or in this vector? That'll return true only if every single element isn't missing. Okay? That not being said, like if it's just an empty string, quote, quote, and wasn't converted to NA, that'll still come up as true. Right? So all is a good test. And again, like the negation, don't do that. Say x 5 Don't worry about R norm. R norm is literally just making random normal variables. It's just a way to make fake data quickly. That's all. Okay? Are all of them not NA? False. We have NAs in there. Just going to put R norm 5. So these are 5. It's true. These 5 variables, they just happen to be not NA. Right? So I want to discuss the difference between these two operations. So, is NA? Yes or no? It's going to say, is it NA? If it's true, if it is missing, it'll say true. Negation, it'll turn all the trues to falses, all the falses to true, which means, is it not NA? This statement here. Then the all says, are they all not NAs? Okay? That's what this statement does here. This statement says, is it NA? Right? Yes or no, yes or no. All, we'll collapse that all into one logical yes or no. So if they're all missing, that'll be true. If they're not all missing, that'll be false. Then the negation out in front will flip it. Are they not all NA? Right? Which means, are any of them NAs? Is there at least one NA? Right? So the order in which you do things matters. Right? So this means, is it NA? Not. Is it not NA? Right? That's what this not does. Are they not NAs? Are all of them? That'll come true if you have data in every single cell. So like there is an all, there is an any. Are any of them NAs? Right? Do we have any NAs and As? So these are just kind of complements to each other, just different ways of thinking, right? If I say if any is that NA equals true, there's at least one NA, right? So any can be thought of as at least one. And not all, right? When we negate all, you can think some. Are some of these falling into this condition? Okay, so that might have made things more confusing. I don't really know. But when you're, I don't know, when I was speaking this out, that kind of made it sound more confusing. When I'm writing them in code, for some reason, it sounds more logical, right? Because I know what I want to do. I know what I want to find. Find the NAs. Are they all NAs? Are they not all NAs? Something like that. So, yeah, I don't know. Brain to mouth malfunction. So complete cases. It returns true if every value of a row is not missing. Okay, so if a row has all data in there, for that record, it'll come as true. Complete dot cases, let's say you have 100 rows by 10 columns. Complete dot cases will be of length 100. Okay? So it'll be one record for each row. So if you have any missing data in there at all, complete dot cases will be false. If you have no missing data in there at all, complete dot cases will be true. This is a good condition, but it's very stringent. It's kind of a shotgun approach, right? Because if you have one column that has like 90% missing, and it's a column you don't even care about, why do you care? If you don't care about that column, you shouldn't be including that in the complete dot cases. You should subset your data first, then use complete dot cases on the subsetted data set. Okay? Yes. Okay. There are different types of missing data, right? So we said, not missing data. There's one thing for missing data, but there are three different ways to kind of say things that aren't really a number per se. So there's NA. We don't know what it is. It's missing. NaN stands for not a number. When you divide 0 by 0, you might see NaN. Infinity and negative infinity. When you take a positive number, divide by 0 or a negative number divide by 0, those are in R. Those are actual things that will come out in a vector, right? So if I say 5 divided by 0, is that greater than 5? Yes. Little known fact, infinity is greater than every number except for infinity. But I think in R, I don't know exactly. Don't do comparisons on infinity. It's confusing. Infinity is a confusing number in general. It's not even a number. There are different types of infinities. We're not going to get into that. But in R, if you divide by 0 from a positive number, it'll give you infinity, negative number, and 0. If you try to do the mean, whoa, not that mean. It's going to give you not a number. If I say 5 and 0 divided by 0, the difference is, although it is not a number, if you use na.rm in all those functions of summarization, it will exclude mean, it will exclude, NAs and NANs, and I believe infinities. Nope. So, yeah, because there are strict, so I guess technically, as long as it's a finite number, if you divide infinity by a number, it's still infinity. Pretty much most of the time, you have functions that you would exclude these missingnesses in there, where NA, you have an is that NA function. Similarly, you have an is that NAN. Say, is this not a number? Did I divide by 0 by accident? This is some of the problems when sometimes you take ratios if something's already 0. Infinity, and similarly with infinity and negative infinity, there's a function is that infinite. So you can subset data that is infinite out, or you could set these infinites to NAs or something like that, depending on what makes sense in your data. Is dot finite returns false for all missing data and true for non-missing. So no matter what it is, if you want to use a kind of a ballpark approach to say, like, do we have a number here, or do we have something that makes sense? So we can have NA, NaN, 5, infinity, negative infinity, right? Is dot finite x will only be true when you have a number in there. NaN is gonna return false. Infinity is gonna return false. NA is gonna return false for that. Okay. Sadly, though, that is not the opposite of is that infinite. Right. Okay. Pretty much, at the end of the day, if you want to make sure you're subsetting any type of missing data whatsoever, is that finite is the approach you want to go. Okay. So if I want to say which ones are valid data, give me a true for that. Oh, sorry, I'm just going to use is that finite. Is this data, is this like numbers, right? That being said, if you subset based on this and you accidentally divide it by 0 somewhere, that data is going to be gone. Okay? Because certain things are important for that. Sometimes people like to not code things well and wait, they accidentally put it in 0 when they mean missing. You start to create a BMI, a height measure. Put height to be 0. You try to create a BMI measure with ratios. You get infinite BMI, right? If you drop them out, you're not going to notice that data is missing or should be missing, right? Again, so when you do logical operations on NA, you get NA because we don't know the answer. I don't know if that's greater than 2. I don't know what that number is. It's just going to give NAs. If you use which x is greater than 2, it'll only return the trues, so it'll only return the element 4. So if you put which on this, and you have missing in there, which doesn't care, which says, I'm only looking for trues, I don't care about falses or missings. So, again, you don't do this. So what you have to do is if you want to say, is x greater than 2, and it's not missing, that's the way you do it with the logical operation. Does that make sense? Right? So if I just say, right before x greater than 2, we had everything but NA was here. Here we have x greater than 2, and it's not missing. That is filled in to be a false. Okay? But again, if you use which, it only grabs trues. If you use filter in dplyr, right, it will exclude NAs. So if you use this condition, right, it'll only grab the fourth element. If you use this the fourth and fifth element. If you use this condition, it still is only going to grab the fourth and fifth element. But for example, if you want it to be, I want to keep things greater than 2 or if it's missing, right? If it's x greater than 2, or take out the not, is that NA, you have to do that if you want to keep the NAs in there, using filter or which, for example. So, missing data with logicals. So here we want to say is x equal to 0 or x equals to 2. Again, it doesn't matter what operation you're doing. If missings are in there, it says it's missing. So you have to put this qualifier saying that it's not missing. Right, so is it equal to 0 or is it equal to 2? This one's 0, this one's 2, and it's not missing. It takes this NA and converts it to false. So we got percent and percent up next, but so by the rules of logic, anything or a true is always true. Doesn't matter if this was false or true. It didn't matter. Doesn't matter if it's true or false. If you say this or something true, it's going to be true. That's why this works. That's why this thing is replacing, right? So right? And what I mean by that, NA can only take in false or true, or it could be true or true for this statement. For this statement up here, it's these are these conditions. It doesn't matter. It's always going to be true. That being said, NA and true is undefined. Because if this NA was true, was in nature, whatever, in the real world, false, this will come out false. If this is true, this will come out true. It doesn't know which one it is because that data is missing. Similarly, true and false, false and false, always returns false. That's why NA and false will return false. Because it doesn't matter what this NA is. You do a logical operation with an and one of these conditions is false, it always comes out false. That's why you say this, and it's not NA. NA is over here every time. Every time come up false. So when we're doing this AND operation, doesn't matter. It says NA. It says whatever this is, it's NA and a false here. Now I know that I can put false in there. Okay? So, percent in percent. Probably one of the most useful things for subsetting data. So you say x percent in percent, and then put a vector of things you want to match against. So I want to say, is x in 0 or 2? That'll return true if x is 0 or 2. Doesn't matter if I repeat it. I can put 0, 0, 2, 2. It doesn't matter. It's okay. We'll say, is that in this lookup list on the right? That being said, NAs are always false in this operator. Okay? Note, the second element doesn't say anything anymore. If we did equals this or this, we have an NA here. We had to put this little qualifier here. Here we don't have to do that. Percent in percent, NAs are always false in the output. So this is good for filtering. So, using the filter command, it doesn't matter. They're always going to give you the same thing because NAs are treated more or less as false when you use filter from dplyr. But a lot of times, you're not doing that. You're doing something where you want to say, is my vector ID, are these is the IDs in this subset of IDs or something like that, right? So when you want to do a lookup with a bunch of ors, right? And I mean ors in this or this or this or this, percent in percent is the way to do it. Okay. No, you would use x is greater than 5 and x is less than 10, and it's not enough. But again, if you're using the filter command specifically in dplyr, even though the result will come up as NA, it'll only look for trues. So that's not going to be a problem in the sense if you want to filter between greater than 2 and less than 5 and you want to drop the missings, it will do that appropriately. All right. Why does it say never? That shouldn't be. So, sorry, this statement's false. They have changed some of the behavior. Not that much. Maybe this was just wrong to begin with. So, oh, sorry. So that's just wrong. Okay, this statement's completely wrong. If you put NA in there, it will return true if there's an NA in there. Sorry, what I mean by that, if you put a NA in the lookup list, say, is X in this, it will return true. Again, if you're doing stuff with NAs, you're getting NAs back almost all the time, unless you have some specific logical operations where it doesn't matter what that value really means. X plus 2 doesn't understand. X times 2 doesn't understand. Right? We don't know what missing plus 2 is or times 2. Okay? So that's missing data in a nutshell. A lot of times, percent in percent. I think somebody had asked, like, what if, for example, we were using boy, girl, dog, cat, or whatever. What if you wanted to exclude things that were not in boy or girl and call it missing? Right? I think that was a question. So, boy, girl, cat, dog. Okay, right? A boy, girl, cat, dog, and a missing value. X percent in percent boy, girl. It'll come up true for only the ones that are boy, girl. Now, I can put not. I can negate that whole statement, right? I can switch the trues to falses. This is saying X percent in percent boy, girl, not everything else. So things that aren't in this list. Things that aren't boy, girl will come up true or false. Or will come up true. So, we do this. X, subset the trues, things that aren't in boy, girl, and set it to missing. Now we can create our factor, where it's boy, girl, or missing. And everything, NAs, anything that's not within boy, girl, will be set to the missing level. Okay, so again, X percent and percent, it'll match against boy, girl, or whatever we give it over here. Come up true if it's in this set. The exclamation point negates that, so saying anything not in this set, and then we use the brackets to replace those values with missing. One last thing about factors. So now we have X. Okay, FX. All right. Boy, girl, missing. Here's the big difference between factors and characters and replacing things. The fifth one is missing. I put it to be some other character. Right? That character, this thing, is not in the levels. It's an unknown level to this factor. It's a new category. So when you try to replace it, it says warning message, blah, 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 invalid factor level, NAs generated, which means you defined a factor, you made a new level that you never told me existed before, you try to jam one in there. It's not going to work. I'm going to warn you, but I'm going to make it missing. So the way you would do this, let's go back to fx. As that character fx, right? Replace it. Let me go back up. fx5 is hey. fx is factor. Levels equals boy, girl, missing, and our new level. Hey. Okay? So you cannot put. So although factors are very similar to characters, they have levels, and if you try to replace things with a level that doesn't exist, it will warn you and make it NAs. Okay? Because it says, hey, you defined the categories before. You're trying to pull a fast one on me now. You have to be explicit, turn it back into a factor, and remake the factor yourself if you want to create a new level. If hey was already in there from the get-go, even if no data was in there, so let's go back to this. Factor x. Note, like I said before, if you make levels and you do a table on it, even if there's no records in that, by default, it will say levels. There's none in this case. You defined a level, none of them showed up. Now, no warning, because this was a level in that factor. So if you try to put new data into a factor that is not part of the levels of that factor, it will not work. It will make it missing. On the flip side, if you create levels where none of them exist in the factor, that's okay. But your tables will still have them in there. I think you can say there is a way in table to, I think, drop. There's a way, I believe, to drop the levels, but we're not going to go into that. Usually, you would just redefine the levels, but most times, a lot of times, you actually want that 0 to come up. All right. Table. Unique gives you the unique values. Table X gives you a one-way table. We talked about this. Use NA equals if any. We'll have a row for the NAs if they exist. Use NA equals always. It'll always have an NA in there. The default behavior is to drop NAs from the table. Table XY will give you a cross tabulation of X and Y, a two-dimensional table. So again, unique will return NAs. So we did a unique on X. These are the unique values. It doesn't sort them by default. So you would have to use the sort command on top of that. What I mean by that is if I say X is 1, 5, and 7, so unique 5, 1, 7. Sorry, it's an RStudio thing. It's not a real warning. It's because my window's so big. It doesn't sort the unique levels. If you want them sorted, there's a sort function to do that. Okay, table. Table, on the other hand, will do sorting. If it's numeric, it will. If it's a character, it will sort them based on alphanumeric. If it's a factor, it will sort them based on the levels. So again, 0, 2, 3, 4. We give a crosstab. Use NA if any. This one doesn't have NA. We've already talked about this. Again, use NA equals if any. There are no NAs in here, so there's no column with an NA value here. And if we say use NA equals always, we'll always have an NA column, even if none exist. Okay. If you use a factor, all levels will be given even if they don't exist. We gave levels 1 to 4. We made this numeric factor. 4 doesn't exist. Even though it doesn't exist, it will give us a 0 there. It'll still make a column for that. And if we wanted to subset it, because it's a one-dimensional table, we can do tab, we call it the table, and we can use subsetting to say which ones are greater than 0. And that'll give us the table with those levels dropped where no data was observed. Okay. Sorry, why did that not So tab, we can do a two-dimensional cross table, and we can use NA equals always. The NA behavior is super important because Fisher's exact test, chi-square test, test of categorical variables depend on the dimension, sometimes depend on the dimensions of the table. And if you include, sorry, I don't mean they depend on the dimensions of the table. I mean they depend if you include the missing data or not. Because if you include the missing data or not, it will treat that as a valid row of the table. So if you have a 2x2 table, two binary outcomes, but if you have NAs in there and include them, and there are NAs, that is a 3x3 table now. Okay? So that's one reason why the behavior in table is to exclude missing data. Okay, so I got two vectors here. We do a little cross tab, and this is two-dimensional. First dimension is the rows, second dimension is the columns, right? So it's technically not a data frame or a matrix, although you can subset them the same way. It is a table class, so it's a two-dimensional table. So margin.table gives you the marginal sums. Okay. Again, when we talked about the apply function, 1 is rows, 2 is columns. Right. The first dimension is rows, the second dimension is columns. So when I did margin.table, the table, and the number 2, I want to take the margin on the columns. So these are the column sums. All right, we're going to do prop.table, and then we're going to take a break. So prop.table, so margin.table does marginal sums. Again, the margin being 1 for rows, 2 being columns. Prop.table does a proportion table, right? So if you leave the margin off, if you don't say 1 or 2, if you don't say anything, you say prop.table, it will do the overall divisor, right? And I mean by that, these are cell probabilities. This is 10% of the entire population. Prop.table 1 means I want to do a cell probability, a cell proportion, based on the rows. So each row should add up to 100%. So 10%, so of this factor x, right, 100% are in factor 1. For a factor, when x is 2, 50% of them, of the y is 2, 50% is 4. Right? So again, this is maybe not the best case. Let's do a more intuitive table.
Can you show us both row and column proportions just to make sure?
Yes, exactly. So I'm going to sample 0, 1. So let's call this treatment. Says 100, replace equals true. Again, just making fake data. Outcome. Okay. Or let's do 3 treatments, just so it's not a 2x2. Okay. So again, whatever's first is on the rows, whatever's second's on the columns. Okay. So prop.table tab just says, of course I did 100, so it's just dividing the numbers. Let's do something that's a little bit different. Let's do 140. Okay, so this represents 17% of the population is in treatment 0 and have outcome 0. Right? So we just took these numbers, added them all up, divided each number by that grand total. Or stated it's the cell means, or the cell proportions. 1, margin equals 1. So let me hit tab so I show you margin equals 1. This is saying the row percentages. So you see 55%, 44% equal 1, 48%, 51% equal 1, 41% equal 1. Okay? So all the rows should add up to 100%. By that I mean proportions, not percentages, right? Okay, I know there's not a way to get them as percentages, but you can always do times 100. So these are percentages now, add to 100. Okay, so 1, again, it does the denominator based on the row totals, 2 based on the column totals. So it's set, so let's go back. So these two, this number represents, of the treatment group 0, 44% of them had a positive outcome. Let's say an outcome of 1. This means of the outcomes that were 1, 26% of them happen to be in treatment 0. Okay. Different interpretability based on the denominator. Then we're going to do fun things like Fisher.test tab. Does the Fisher's exact test of independence. Chi-SQ, we'll talk about that tomorrow, I think. Chi-square test of independence on the rows and the columns. But you input these table objects. All right. When you do the testing? No. That's a good question. They don't do that by default, and they don't do that at all. For example, it doesn't do. So it's possible to do. Kind of roll your own in some respects. So what it does, what I did here, is I did the margin table. Right? So that'll give me 3 rows, three numbers. Row totals. And I did that for 1 because I wanted rows. Now because I wanted to bind on the columns, I wanted to bind on the columns because I did the margins on the rows. Right? So if I wanted to do, for example, total. So these are kind of flipping because I took margins over the columns, right? That'll only give me 2 numbers. So I want to put those numbers as another row, so I R binded it. I'm row bound. Then, so let's call this tab 2. Let's do tab 2, tab 2, tab 2. You can have them all if you like. But no, by default tab, there's no like row, col, all, for example, like there is in Stata. Especially because let's do a chi-square test. They're doing completely different tests. The table you input into the tests that we're going to be talking about later for categorical variables do not have the margins included, right? So they are the kind that table comes out. If you add the margins, it doesn't say, hey, these are marginal totals or row totals or something like that. We're going to disregard them. It does not do that. It still thinks this is part of the data, right? And does a p-value based on this. So this p-value is based on a 3x3 table. Or sorry, 3x4 table. This one is only based on a 2x3 table, right? And you can note that degrees of freedom, right? Rows minus 1 times columns minus 1, right? So if this one's 2 by 3, 2 minus 1 is 1, 3 minus 1 is 2, multiply them, degrees of freedom is 2. And this one is a 4 by 3, so you subtract, you get 3 times 2, you get 6 degrees of freedom. But this is not an that is totally invalid, right? That statistic and p-value and all that kind of stuff because you added data that's not real, and that's not just how they work. But you can do it. So I'll post this somewhere so that you can see. All right, let's take a 5-minute break. I think it's been pretty long. Also, yeah. Yes. It's okay if you don't put them in the script, just as long as you have the code. Also, you can say export, and you can say, yeah. Yeah, just one big attachment. Yeah, so just do that. That's fine. Or you can just give the code. It's not just the code. Oh yeah. Sorry, don't worry about that. I'll make an announcement about that. Yeah, don't worry about that. Last time we tried to have people use that markdown format. Yeah, no. Well, no. So try file. Go to RStudio file, new file. Up top menu, file, new file, or markdown. Just say yes. Install new package. And once it's installed, there's going to be a button up there that says knit. And make you save that file. Try it, just to see what comes out. Yes. No. You don't have to worry about that for your homework. But for kind of reports and stuff later, it's a relatively straight. It's just a way you can copy or paste the code in there and get the outputs for example. So once those are installed, you should get a file pop up to save it. Yep, that's fine. Let's just click HTML for now. You can switch it later. So click OK. It'll make something. And then click the little button. Say save it somewhere. So save it somewhere. Delete it later. It's not a big deal. And save. Run. So this is if you scroll through it, you see there's a drop down. And if you close it down, you look at the actual hard markdown file. You see the code that was used.
Well, we're not going to get to that level of complexity, but just know that.
So you can see this if you scroll down.
If you want to dump here some of that, you might need to see someone.
No, sorry, in this. So this is all the code and the text that was used in here. So if you start changing that up, you can see how it changes. And if you click the down arrow next to the knit button, you can see if you want to knit color.
Is there a signage for that?
They may not come around with one, so I don't think so.
I just wanted to make sure I didn't miss anything.
No, you didn't. So I'll have to email them about.
And now I'm trying to
Yes, I'll do it right now.
Okay.
I'll do it at the end of class.
Okay.
Oh, by the way, so there's a couple little pieces of confusion. There is data camp modules and try-R modules for the homework 0, and then the second thing is you don't need to knit anything for your homework 1, or the homework that's assigned right now. Don't worry about that. Just submit the R code. If you would also like to submit the plot that is associated with it, that is fine. Just send that in an email. Yeah.
So, when you do y-OS, it's saying that you have, it's assuming you have a data frame also supplied to the function, which has columns X, like the name of the column is X and the name of the column is Y. And it's saying, I want to plot Y as the outcome variable, that's why it's on the left-hand side of the column. And I want to plot sort of the groups on the x-axis are defined by the x column. So the way that this is saying, I want to make one box plot for the y variable and another box plot for the x variable. Yeah. The default, I think the default is to be closed on the right-hand side, so 10 would be included. It would be like greater than 0, less than equal to 10. The break's always defined on the right-hand side. But the way that you can tell is when you run the cut command and you print it out, you'll see the levels are, they'll give you, the parentheses for fragmentation, and it'll tell you, that will tell you which kind is included in the row.
Yeah.
I'm trying to go up.
Mm-hmm. So you are in your day 2 data. Yep.
I want to go to day 3.
Okay.
Oh,
Say
yeah, I should
say day 3.
I should put day 3.
So hit tab real quick. So day 3.
Oh, okay.
Scroll down. Hit enter. Let's hit tab. So hit enter there, and we can get rid of everything after that. I'm going to show you. Yep, perfect. Try that.
Perfect.
There you go.
Alright,
Yep.
thanks.
I've never tried or used, like if I wanted to for the exact test result, I've never tried to input a data frame. I've always input a table. But you could theoretically, have the data frame with 2 rows and 2 columns, which is almost the same thing as a table. I've never tried. Yeah. It would be data frame. You use the table function in case there are columns in your data frame that you want to tabulate. Because like you might read into data and you have for gender. And if you want to tabulate that, then you have to do table, data frame, dollar, gender. But for reading the data, you'll always read it as a data frame. And then usually when you work with tables, you work with certain columns. You can tabulate more data, and you can also tabulate it. Like inside the table, like the result of the table, you only have numbers in there. Right, because what you want to do on gender is count them, so the result is gender. Right, you might have male and female, those are words, right? But what you want to do ultimately is count the number of males and count the number of females. That's what you do with data. You can do it with the table functions. To do the computation, to do the calculations, yeah. It is. So the result don't get too caught up with that though. Just for you, like whatever you want to calculate, think of the table function. This table is a function. And you just want to input to that function.
All right. So we're going to be moving on a bit to some salary data. And we're talking about one of the drudgeries of data cleaning, which are strings and characters and text. They are more or less a nightmare in a lot of respects if your data is not formatted well. So we'll be going through some of those nightmares in this. So we're going to read some of the data from the Baltimore City salaries from 2015. So we're going to use the readr package, and we're going to read the data in, and we're going to change the first column name to be name. So let me just run this, show you what comes out. So here's a little view of the data. Name, job title, agency, agency ID, hire date, annual salary, gross pay. To a human, those look like numbers. They are not numbers to R. They have dollar signs in there. They may have commas in there. And R doesn't assume that's some sort of money type. Neither does mostly any other system, for that matter. So we just called the first one name. Again, let's do any and all. So, are any of the names missing? No. Okay. So we know we have names for all the people. We didn't check to see if they were an empty string, but they weren't encoded as NA when it was read in. So one of the big things you always want to do is recode variables. So base R, right? Gender could have been coded male, M, female, capital F, lowercase f. Using Excel, to find all these, you have to be filtering, changing them by hand, or some sort of if statements. So gender, let's say, is a column. So data gender, we're going to bracket. Right? We're going to do some subsetting because we want to do replacing. We're going to say, is gender in male, M, or M, uppercase or lowercase? we're going to reassign those all to male. Okay? Right? So this is saying if you're in any of these three, you're going to be reset to capital M ALE. Okay, so again, percent and percent does just a match between the thing on the left and some lookup table and returns true or false. So let's, that was one case. That was like one way we could do it. But that's usually, in order to get these, you kind of have to usually explore the data to see what kind of codings or miscodings have been done. So we made a lovely vector that had kind of any and everything of ways you could put sex or gender in there, man and woman, and male and female. So one, there's a lot of ways you can do this. Some ways make the most sense to how you approach. You could lowercase everything, right? For one, you could uppercase everything, right? That'll at least, you know, this one, this one, this one, this one will all be merged together. So that might be a good first step. So we're going to be talking about just a bunch of different sets of string functions, a little bit of these things called regular expressions, which are like find on steroids, right? So it allows you to do a very, very powerful set of searching and replacing operations. So the first thing we're going to be talking about when we're talking about strings is pasting. So I showed you that gender example because we're going to come back to that, show you how to take things out, replace them, and all that kind of stuff. But if you had, for example, all these cases and you knew which ones you already had, you could just have done this just the same, just putting in that long, larger vector of the things you want to be recoded as male. But we're going to show you some other functions to work with strings because we're going to use those a little bit later to kind of paste things together, take things apart, subset them, substring them. So paste. Paste concatenate strings together. So this function, this line of code, paste visit underscore 1 to 5, the separator being underscore. Visit underscore 1, 2, 3, 4, 5. Okay? Paste them together based on whatever separator. If you don't specify the separator in the paste command, its default is spaces. Okay? So it would be visit space 1, visit space 2, visit space 3. So there's a separator argument and a collapse argument. Separator says take this, and what do you want to separate it by when you put them together? It still works here, but collapse, if you specify that, it joins it all into one big string. There are 5. This is a character of length 5, a character vector with 5 elements. This is one character string. One big one. It took all these, pasted them together with underscores, and then it put the whole big thing together and separated by spaces. Okay? 2 different operations. One, put them together, but keep the number of elements the same, or at least some combination. Collapse will say put it all together into one big thing. So paste 2 is going to be, we go to the store. And we separate it with, we don't have to separate it with just spaces, or commas, or quotes, or whatever. We can separate it with words. So it says today is going to be the day we go to the store. So at the end of every string, it added day and then a space and pasted this all together. Right? Note also, this is still one big string. Okay? So these 3 examples demonstrate different behavior. One, you give it one vector and a vector of length 5. It says repeat that 1 5 times and paste them together with the separator. This one says do that same thing, but the fact that we said we want to collapse this whole thing together in one big one, collapse does that. This is not to the function, we are passing in 3 different strings. Not a vector of length 3. Right? So I want to demonstrate exactly what I mean. So I'm passing in 3 different things. versus one thing of length 3. So to R, think of them, so they're not named, but think of this as like argument 1, argument 2, argument 3, right? X, Y, Z, or something like that in the function. Whereas this, it says paste X is equal to this one big vector. So sep will work when you say, it'll separate by the individual things that you pass into paste. But in this case, you only pass one thing. It's just one vector in there. So it doesn't do anything. If you use collapse, what it'll do is it'll try to merge them all together. So sep, I would say most of the time, I'd say ballpark 75% of the time, you're doing the top thing. You're taking 2, maybe 3 things, and you're pasting them together with a separator, not trying to collapse them all into one big vector. Okay?
I'm looking at the outcome of the last command with the set, the D. I really don't see how it is doing it if I compare it to the one above it. For example, I expected that the D would have repeated all the 3.
Okay, so might be better, might be easier to contrast this one and this one. Okay, so let's not look at the middle one for a minute. So let's look at this one. So this one takes visit, and they're of different length, right? But if you pass in only one thing, it repeats it as many times as the other. So it's visit separator 1. Put it with the 1. Visit separator underscore 2. So on. Here it says it's 3 different vectors, all of length 1. Right? 2 is 1. Is going to be is a different one. We go to the store is a different one. So it says take this, paste it with this one, and paste it with this one. This, paste it with this, paste it with this. In this case, it was visit and 1, visit and 2. This is like visit, 1, and a different string that we're pasting together. So then it says take this, and it says you want to paste things together with a separator. What is that separator? That separator is the word day and then a space. So it says 2, puts the word day, puts a space. Paste that together with this string. It says is going to be gets to the end, puts the word day, puts a space. We go to the sort. So if I put whatever I put as the separator, so visually look at this. See where these quotes end and these quotes end? Whatever's kind of in between here, or whatever is in here, whatever the separator is going to be put here and here. Right? So I put a comma there, for example. So it says 2 gets to this thing. What's the separator? Puts a comma. Put the next string in there. What's the end of it? You're going to a space. I'm going to put a comma.
So if you wanted it to repeat it in the tail.
If you wanted to repeat it?
You have to repeat the comma.
In the tail.
In the tail.
Sorry, say that one more time?
If you wanted the comma to be repeated in the tail item, what would you have done?
So it won't. It says it'll only put a separator between things, right? There's nothing at the end. So if you wanted to say, okay, put one at the very end, you have to put something to paste it together. It's a good question. Yeah. So sep by default in paste is quote. A space, sorry. So, okay, so there's this, and then there's this. Come on. Okay. Again, contrast that with this. So, collapse takes in a vector and collapses that vector. So sep is related to when you have multiple things that you want to put together that are separated, that are different vectors, right? So although we didn't put C around it, this and this and this are separate vectors, right, to the function. We're putting in this one and that one and that one. This one is one big vector, right? Sep doesn't operate on this because it's one thing, right? It's one LX. Collapse works on that. So sep, most of the time you're trying to do paste this and this together with some separator, right? You're usually trying to do, like I would say at least 90% of the time what I'm doing is this. Sometimes when I want to make a long string or like a sentence or something like that, I'll be using collapse, but I'd say 75% of the time you're using sep, and you're putting in multiple vectors. Collapse, generally, not exactly, but a lot of times I'll put in one vector with a collapse, and it'll paste them all together. Let me see if the help file is any more helpful than that. I guess not. Yes, did you have a question?
Yes. I was just wondering, is there another way to do, like, maybe to add a little bit of a string or to strip it at the end or something like
Give me an example.
like the dollar signs because you just strip that?
Yes. But yes. So that's a totally different operation. That's not for pasting, but yes. So we're gonna sub them out. So okay, there's paste and paste 0. The main difference between paste and paste 0 is the default in paste 0 is to not separate things by spaces. So you see here, I say paste 0. It's visit 1, visit 2, visit 3, visit 4. This thing is annoying. Okay. By default, paste. You don't give a separator. It says, oh, you want to paste things by spaces. A lot of times you don't. Paste 0 was created so that, just as a shortcut, more or less, that says paste sep equals nothing. So paste pastes things together. By default, it assumes you want spaces. Paste 0 says, I don't want any spaces, right? And gives you these back between things. So again, paste, you put this vector in there. It doesn't do anything to it. It doesn't put them together in any way, right? Yes, it makes it into a character, but it's any result of paste is going to be a character. Paste 1 to 5, but when we say collapse, it actually takes all these and collapses it by spaces. Puts it in. So again, vector of length 5, one big, vector of length 1. So we talked about paste and paste 0. 2 upper, 2 lower. We'll make everything uppercase or everything lowercase. str trim will trim the white space at the front and the end of a character. So if you have like space, your name, and a space, it'll take the white space at the beginning and the end. But if it was like space, John, space, Michelle, space, it'll only take the spaces at the end. It won't do anything to the space in the middle. It won't concatenate John and Michelle together. Trim WS, after all the versions of R you have now, that is included in base. Trim WS, trim white space, will trim the beginning and the end. This was a function in a string R package, which we're going to talk about today, string R, but they included it as an inherent function when you download R now. So trim WS, if you want to get the white space out of something, that's the way to do it. I'll show you an example in a minute. So again, RStudio, how they book them, or this package called string R. So it makes some things more intuitive. I grew up on 2 functions that I'll talk about, grep and gsub, which is for regular expression matching and regular expression replacement. So if I say, like, I want to replace everywhere you say John with the word, cat, right? Gsub will substitute those. Or if I want to say which of these strings has the word John in it, grep will do that. String R is a much more intuitive, a much more standardized set of functions that are a little bit more explicit that was written. It's different than base R. It's used a lot for answers. It has a standard format for most functions. The first argument to every function in string R is the string you want to like either do a replacement on or do the matching on. That is not the case for the functions in base. Why is that important? We're teaching piping. Piping assumes the first argument that you pipe in there is the one you want to pass in. Right? So remember, filter, all that kind of stuff. The first argument was the data set. So you take the data set, pipe it in. String R, you take the string, you pipe it into the string R functions. That's not the case for the base functions. The only reason, in some respects, I still use the base functions is because I've been using them for about like 7 years, and I can't, once you figure out a way to do something, it's really hard to change. So R can do a lot more than find exact matches for a whole string. Perl and other languages, it uses regular expressions. So what are regular expressions? It's a way to search for specific things. It's they can be very complicated or simple. It's very useful, but sometimes it can be a bit complicated. Right? If you want to find just a straight word, if you want to just find an exact match, no case, like the exact case, all that kind of stuff, that is blaringly simple in R. But if you want to say, I want to find the letter J, a bunch of letters, a space, and then the capital letter M, and then a bunch of and any bunch of letters, you can do that. You just have to use a regular expression. So here's a little reference for regular expression. These are the most important operators, more or less, that you have to know. So a period matches any single character. Space, the number 5, a letter, uppercase, lowercase, doesn't matter. Star, asterisk, means repeat as many times, even if it's 0, of the last character. So let's say I want to look for, if you've ever heard of the umbrella game, right? You look for words that have double letters in them, okay? But let's say I want to look for a word that has double L's. So let's say apple, umbrella, so I want to say I would look for L star. Sorry. Oh, that's not much. Sorry. So it's looking for a match of the last character. So either it is a let me make this a little bit clearer. All right. We're gonna go with some of these with respect to examples. So we're gonna talk about these two. Question mark, we're not gonna get into too much. But here's the one. So I'm gonna show you specific examples on how to do some string matching, which will be a lot more clear. The caret says the start of a string. Okay? So you want to find things that start with the letter A, for example. You say caret A. And that says, out of X, right, the only string that starts with the letter A is apple. Right? If I say, still only says 1, it's saying exactly match the very beginning of the string, the letter A. Okay? So caret matches the start of a string. The $sign matches the end of a string. So you're saying, I want to look for a word that ends with the letter B. Say B $sign. Okay? So we'll get into those in some of the cleaning and some of the examples here. So many times what you want to do is substringing or splitting strings. So str sub, you take in the string. You want to know where the start of the string and the end of the string. So let's say you have dates, and don't feel like converting them to dates or anything like that. But let's say you have IDs. And you say, I want to get the first 4 characters. The first 4 characters, for example, represent the site that they're at. Right? You would say str_sub, that ID variable, 1, 4. So grab the first 4 characters. Sub str substring in base will do the exact same thing. Start and stop. Split. We'll split on a pattern, but let's look at a substring. Substring str sub x 1 4. So it grabs the first 4 characters of any of the strings. Note, boo only has 3, so it just returns the whole string back. Okay? So you just want to subset the string, not based on anything, just based on the number of characters, completely. Sorry, I didn't. In that one slide, end card, yeah.
The one you just did, what is that
Ooh.
1.2 in the?
I want to start at the first.
It's just pointing us out at it to start. Oh, okay.
So it start. Sorry, where do I want to start in the string? So if I wanted like the 3rd to the 5th, I'd say 3 5. That's a good question. Yeah. So first, I want to go from the first letter to the 4th letter, if there is a 4th letter. So ncar tells me the number of characters in a string. So I could do, for example, I want to go from the 2nd letter to the very end. So this will return the number of characters, or kind of the length of the string, right? And I will substring from the 2nd all the way to the end.
Can you do math with that? Could you do like ncar minus 2 or something like that?
Yep. So boo didn't have any, right? So it tried to go from 2. So ncar minus 2 is going to be 1. So it doesn't go. If the end is less than the start, it will not return anything. Right. So just to be clear, what I mean with that was this for boo will return 1. Right, 1, and so it's like saying it's trying to go from 2 to 1, and says you're going the wrong way, right? Okay, so that's substringing. So in base R, str split, or in string R, str_split, you put the string and then you put the pattern. It's the exact same syntax. So that says I want to split up a string. So we're not going to be able to use x anymore. We can. Sorry, x. I want to split on whenever I see an L. Right? A lot of times this is like a space or a comma. So I can split on a space, for example. I might split on and so let's look at these two. So I'm splitting on a space up here. So 1, note, whatever you split it on, it's removed. Okay? I'm saying that this space is gone now. Right? And similarly, if I split on the exclamation point, it's gone now. It's split it on that. It says I found it, and I want to split the thing on the left and the thing on the right. And I'll give you, and you'll note, this returns a list. Right? In this case, all 3 of them have two elements. Right? Down here, the last one didn't have an exclamation point, so it only has one thing. It says I didn't split anything. I didn't see an exclamation point. There's no split. So this allows you, so string split will allow you to break up a string based on some criteria. And it doesn't just have to be, one. I have multi-spaces. So it splits on every single space. Right? So it says I sees a space. All right, I'm going to lop that off. Have sees a space, lops that off. and gives you back a list.
I'm confused about what that is becoming now. So is that like a new vector?
That is a list, right? So that is a list of, so the reason it's a list is like we just showed, everything has different lengths, right? You can collapse those things together. We'll get to that a little bit later, but like that's one way you can split up words and do some manipulations, either substring it or split it together. Again, I really like writing. String or split, you split it, everything's broken up based on the spaces and it's deleted. Again, using string R, exact same syntax, it gives you the same exact output. Note. Remember before I said the period matches anything. Periods are special, dollar signs are special, carets are special. Okay? Because they matter with respect. So, periods, asterisks, carets, dollar signs are special characters, right? Because they mean something in regular expressions, right? They mean any character. They mean repeat this thing multiple times. Question mark is also special. Dollar sign means the end of a string. Caret means the beginning of a string, right? So if you say str split and you put a period in here, what R sees is split on anything. Split on anything. That's what period means. So if you want to split on things like periods or dollar sign, which that data set we obviously showed clearly have, we have to use this fixed command. Say, this is not a regular expression. Don't treat this special. It is not special. We want you to exactly match a period.
Does the base R have the same data?
It does, but you don't use fixed, it will not work.
And you just have to escape.
You have to escape it, or there's the option fixed equals true as an argument. But for the most part, I'll be going through and using the string R functions for the most part. Okay, so again, using lists, you can use the double brackets, right? Y bracket 2. It was a list, and we can grab this vector, like writing. Right? It was split into a list. We can grab the second one, right, from back here, like writing. We split it based on spaces. It's a list. We can grab the second element. Now, lists. We breezed over them very briefly, but there are other apply functions. So there's two functions that are important. L apply and S apply. L apply takes in a list or a vector and applies a function and returns a list. S apply does the same exact thing, but it tries to simplify the output if it can. So what this will do, S apply on Y, it says every element of the list, right? Element 1, it says element 1 is I really, second one is like writing, third one is R code programs. Okay? S apply is going to go to the first element, I really, and we're going to take the first one. The first element of that vector. So remember, I really, the first one is I. Like writing, in that element, in element 2, the first element is like. Writing the third element. So I'm saying, first one is this, first one is this, first one is this. That's what this is doing here. It's going through every single element of that list and grabbing the first element. That's what this code's doing. And because what's returned is just one vector, one number, one character, right? It's going to say, S apply says, all right, you're giving back just one character. Let me simplify it. I'll just give you a vector back. Great. So it gives the first one. Nth does the same exact thing that we talked about before, except instead of the first, it gives you the second. Right? If we go back, second one is really writing code. S apply, grab the second one. Last, we just take the very last one. and it simplifies it into that. So, reason why we had to talk about lists in some respects is string splitting will give you lists back. All right. So, a lot of the times you're not necessarily doing it this way unless it's more intuitive, unless it's easy to kind of split things, do something, and join them back together. A lot of times you're using regular expressions. And for the sake of time and simplicity, I'm going to use the string R functions. So there's str detect, and it returns true if a pattern is found. So let's say it's a bunch of names, and you're looking for the name John. You say str detect, you put in the string, you look for the word John, it gives true if John's in there, false otherwise. Okay? If you say caret John, that'll return true if those character strings start with the word John. Okay? So what I mean by that, so true. So let me Mr. John Doe still return true. John is in Mr. John Doe and John Michelle. If I say caret John, it only returns true for the second one because that's the start of that string. You want to end in the letters li and then the end of the string, it will return true. So str detect gives you true falses if that string is found. Okay? str subset will do something very similar, except it won't give you logicals back. It'll only give you the strings back where it was true. Okay? So str detect gives trues or false if you find the pattern. str subset is kind of a shortcut for x bracket str detect. So it says, okay, find the ones where this condition is true, and then just give those back. Give those ones where it's true. Right? So if I do these, again, with str subset, it's only going to give those back. Again, note, this doesn't correspond. So this gives us the strings back, but it's not necessarily the same length as the vector we gave in. Right? So what I mean is if I say names, bracket str detect, it's the same thing as just saying str subset. Okay? So all it is saying, not just give me a true false where this condition is met, but actually give me the vectors back. str extract will say, hey, find this pattern, but only give me that pattern back. And I mean that. So it says extract John, right? The first two have the word John in it. The third one doesn't, so it returns missing. This says grab only li where it's at the end of the string. So, for example, right? If I run this, the last one has the letters li, but it's not at the end of the string. So it won't be matched. That's what this dollar sign is doing again. So str extract will extract that specific string. But, sorry, last thing, J star. You can start doing things like J dot star. J means, so you want to find the letter J, capital J, period means any other character can be after that. Star means repeat it as many times as you need to, and then I put a space here. So find a word that starts with J, and then there's a space. Okay? Then return that. Right? Return the thing that matched that. Right? So if, for example, so here, let me make oh, no. Sorry about that. I replaced it. So look for the letter J, look for any character, repeat it as many times, and then it needed to find a space. Okay? So, found J, found OHN, found a space. And it said, give me that back. Here found J-O-E, then found a space, return that back. Yes?
What if you wanted to return the full name, like Mr. John Doe and John Michelle?
So you wouldn't use string extract. You could use string subset. So string extract will extract only the things that were matched. Right? String detect says, do you see anywhere in these strings the capital letter J, some amount of letters or numbers or whatever, and then a space? If so, give me a true. String subset will say yes. Give me only the ones that are true, but I don't care if it's true or false. I actually want to get back the strings. Yes?
Is it possible for you to send us a text file with the console that you got from today?
Yes. Yeah.
I'm not gonna remember.
No, that's so. They are detect and subset essentially do the same thing, just give back different results, and subset might not be the same length as what you passed in. Detect will give you logical trues or falses. Subset will say, hey, which ones actually match? And I'll give you the whole string back. Extract says, find these things, and where you find them, give me that match only, not the whole string back. Okay? So extract actually grabs things from inside the string. Subset is talking about subsetting that vector. Detect is just a logical. In this vector, where do we find this condition? Subset is where we find that condition, subset that vector, but gives us the whole string back. Extract says, find the things, and then give me where the matches are. And if there are no matches, give me NA. If nothing was matched, say nothing was matched. But if something was matched, give me what matched to that string. Okay. These are good for finding stuff. str replace and str replace all are what you use to replace stuff in the string. So str underscore replace says find something and replace it with something else. So let's say if I wanted to find where John was and replace it with Joe, I can do that. It would be str replace, pattern would be John, replacement would be Joe. So for example, so it wherever it finds John, it replaces Joe. Okay? So nothing happened to this name, nothing happened to this name. It only says, oh, I found some John, I'm going to replace it. Now, the only difference between that and replace all is str replace will find the first instance of that and replace it. So let me do this. something like that. It replaces John, or it sees John, it replaces Joe. But str replace will only find the first instance and replace it. So John was replaced. It found John, it replaced it. It did not replace this one. It'll only say str replace will only do the first instance. Str replace all will replace all instances, all matches. So again, the difference, str replace, find it the first time, replace it. Str replace all. Wherever you find this pattern, replace it with the new replacement. So that's the only difference between str replace and str replace all. So these are for subsetting and grabbing things. These are for replacing things within the string.
Can you only replace one thing at a time? Or can you replace like a set of things?
Yes. It depends what you mean. So if you want to replace John or Steve with Joe, yes.
So if I wanted to replace, like 3 different ethnicities with other, with the same thing. I see.
So this is within the string, we put an or operator, right? Steve or John or Doe, we're going to replace with Joe. So John was replaced, Doe was replaced, John was replaced, Steve was replaced, Doe was replaced, John was replaced twice. Yes. There is no harm, though, if you are starting out, to do this in 3 separate operations and keep replacing. All right. Nope, not going to go over those. So, if you look at the help for modifiers. So if you Google string, if you load, you have to load. Okay, again, if you want to use these, we have to load the string R package. So library string R. If you don't have it, you have to use install.packages again. But if you look at modifiers, really the one that you should focus on is fixed. So by default, it assumes you're passing in, and we're going to end up in a minute. It assumes you're using regular expressions, but if you want to say, hey, I want you to match this exact thing and replace it with this exact thing, that will work. That is almost identical to find and replace in Excel or Word or something like that. That being said, you cannot use regular expressions within that. So when I did Joe, pipe, Steve, pipe, whatever, that will look for the pipe symbol. That will not say this or this or this, if that makes sense. But you need these. You need this when you're using special stuff. I mean, there is a way to escape this thing called escaping. We're not going to go into that. But if you're, so like that data set that you saw, like I said, it looks like numbers to people, but it doesn't to R because they have $ signs out in front. If you want to find a $ sign, you have to put fixed around it. Otherwise, it's going to say, look at the end of the string, right? Because it's special. All right. Lastly, I think it's in, sorry. If you say str replace, if we look at the help, sorry, maybe it's in modifiers. I think ignore. Okay. There are options in these modifiers for ignoring case. So, let's say I want to look for the word John. Fixed, John, ignore, case equals true. It found John, regardless of the uppercase or lowercase. I didn't have to put uppercase John, right? So this little Little John found John here, John here, John here, John here, and replaced it with Joe, regardless of the case. It says do this, find it, but I don't care if it's uppercase, lowercase, mixed case, whatever. It could have been capital O, lowercase o, all that kind of stuff. As long as it's got these 4 letters together, regardless of case, we're going to be able to match it. All right. So we're going to end today. Yes.
Just for damage control, if you realize that you did something wrong, like you did the wrong place, how can you undo that?
Read the data set back in. So you should have a script at the top where you read the data, start doing manipulations. Read the same. If you've reassigned, so one, you can, if it's a large data set and it takes a while to read in, you can double save it. You can save it as something else and work on a copy. And then if that defaults, you can screw it up. Or sorry, screw it up, you can revert back to the other one, or you just read the data set back in. All right. Email me questions, because this is definitely one of the most confusing parts of it, because strings can be infinitely weird, and also